Prabir, participant they making late to join.
एग्जैक्ट टाइम रे आसी
Okay.
सर नमस्कार
नमस्कार नमस्कार
Sir, namaskar, sir. Sir, namaskar.
नमस्कार 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 ନମସ୍କାର।
ଷ୍ଟାର୍ଟ କରିବା।
ହଁ କରିବେ।
हाँ स्टार्ट
Yes.
ଆଉ କେତେ 29 ହେଇଛନ୍ତି ନା ପାର୍ଟିସିପେଣ୍ଟ
ହଁ ସାର୍ ଆସୁଛନ୍ତି ଆସି
ଆଉ 2 ମିନିଟ୍ ରହିଯିବା ଟିକେ
ହଁ ହଁ ଗୋଟେ
ଆଜ୍ଞା।
ମିନିଟ୍ କିଛି ଅସୁବିଧା
Right.
ନାହିଁ। ଓଃ, ଶୀତ କେମିତି ହଉଛି?
ବହୁତ ଥଣ୍ଡା ପଡିଲାଣି ଏଠି।
ବହୁତ ଥଣ୍ଡା ଅଛି ସାର୍। ଆମ ହାଇଦ୍ରାବାଦ ଥଣ୍ଡା ହଉଥିଲା ନଭେମ୍ବର ମାସରେ, ଡିସେମ୍ବରରେ କମି ଯାଇଛି।
ଆଚ୍ଛା, ଏବେ ସାର୍ ଏଇଠି ପଡୁଛି ଥଣ୍ଡା ଟା, ଆରମ୍ଭ
ହଁ
ହେଇଛି ଏବେ।
ପଡିବ, ସମ୍ବଲପୁରରେ ଟିକେ ଥଣ୍ଡା ପଡିବ।
ହୁଁ,
ଖରା ଯେମିତି ଶୀତ ଯେମିତି ସେଠି।
ହଁ ସାର୍।
ହୁଁ। ଓହୋ।
ସାର୍ ଆପଣ ଭଲ ଅଛନ୍ତି?
ହଁ ହଁ ଠିକ ଠାକ ଅଛି।
ବହୁତ ଦିନ ହେଲା ଆପଣଙ୍କୁ ଦେଖା ହେଇ।
ହଁ ବହୁତ ଦିନ ହେଲା ଦେଖା ହେଇନି। ମୁଁ କାଲି ଟିକେ ନମସ୍କାର ନମସ୍କାର, କାଲି ମୁଁ ଟିକେ ବ୍ରହ୍ମପୁର ଯାଉଛି।
ଆସୁଛନ୍ତି ସାର୍?
ହଁ
ଆଚ୍ଛା,
ସାର୍ ଆପଣ ସୁଇଟ୍ କେବେ ଆସନ୍ତୁ? ସୁଇଟ୍ 6 ତାରିଖରେ ଆସିବି। ସେ ସମ୍ବଲପୁର ୟୁନିଭର୍ସିଟି ଗୋଟେ କଣ ଗୋଟେ ଥେସିସ୍ ଟା ଦେଖିଥିଲି, ତାର ଗୋଟେ ଭାଇବା ହବ।
ଆଚ୍ଛା, ଆଚ୍ଛା।
ହୁଁ।
ସାର୍ ସମ୍ବଲପୁର ୟୁନିଭର୍ସିଟି ଆସିଲେ ଟିକେ ଅଧଘଣ୍ଟା ପାଇଁ ଆମ ସୁଇଟ୍ ଭିତରକୁ ପଳେଇ ଆସିବେ।
ନାଇଁ ତ ସୁଟ୍ ରେ ହିଁ ଭାଇବା ହବ ବୋଧେ।
ଆଚ୍ଛା, ସୁଇଟ୍ ରେ ହବ, ତାହେଲେ
ହଁ
ଭଲ
ବୋଧେ
ଅଛି।
ବୋଧେ ସୁଟ୍ ରେ ହୁଏ ନା, ତାର ସେଟା ସୁଟ୍ ତ ନୋଡାଲ ସେଣ୍ଟର।
ହଁ, ନୋଡାଲ ସେଣ୍ଟର ତ ସୁଇଟ୍।
ହଁ ତ ସୁଟ୍ ରେ ହିଁ ହବ, ସୁଟ୍ କୁ ଆସିବି।
ହୁଁ,
ଟିକଟ ଫିକଟ କରିନି, କନଫର୍ମ ହେଲେ କହିବି।
ଆଚ୍ଛା, ଡେଟ୍ ଫାଇନାଲ ହେଲା ପରେ।
ଆଉ ଡେଟ୍ ମୁଁ ଲେଖିଛି, ଡେଟ୍ ଟା ସେଇଟା ଯଦି ନୋଟିଫିକେସନ
ଆଚ୍ଛା,
ଆସିବ।
ହଁ, ଆପଣ ଯୋଉ ଡେଟ୍ ଦେବେ ସେଇ ଡେଟ୍ ରେ ତ
ହଁ
ହବ ନା।
ମୁଁ 6 ତାରିଖ ଲେଖିଛି, ଦେଖାଯାଉ କଣ ହଉଛି।
ହଁ, ଆପଣ ଯୋଉ ଡେଟ୍ ଦେବେ ସେଇ ଡେଟ୍ କୁ ହିଁ ଫାଇନାଲ
ହଁ
କରିବେନି, ଆଉ
ହଁ
କିଛି ତ
ସେ
ଅଲଗା
ଡେଟ୍ ହିଁ
କରିବେ।
ଫାଇନାଲ ହବ, ଯଦି ଅନ୍ୟ କିଛି ପ୍ରୋବ୍ଲେମ ନଥିବ।
ହଁ।
ସେଟା କନଫର୍ମ ହେଲେ ମୁଁ କହିବି ଆଉ।
ହୁଁ,
କେତେ
ହୁଁ।
ଜଣ ପାର୍ଟିସିପେଣ୍ଟ ଅଛନ୍ତି, କେମିତି ଚାଲୁଛି? ଠିକ ଠାକ ଚାଲିଛି?
ହଁ ସାର୍, ଠିକ ଚାଲୁଛି।
ଠିକ ଚାଲିଛି।
ଏବେ ତ ସାର୍ 32 ପାର୍ଟିସିପେଣ୍ଟସ୍ ଅଛନ୍ତି।
ହୁଁ।
ସବୁବେଳେ ସାର୍ ନିୟରଲି 50 ପାର୍ଟିସିପେଣ୍ଟସ୍ ରହନ୍ତି।
ଆଚ୍ଛା, ଠିକ
ହଁ।
ଅଛି।
କାପାସିଟି 50।
50
ହୁଁ।
50
ହଁ
ଆଚ୍ଛା
ତ 50, 52, 55 ଏମିତି ରହନ୍ତି।
ଆଚ୍ଛା
ବଢିବା
ଆଚ୍ଛା
ପଡୁଥିବ।
ଆଚ୍ଛା। ଏଇଟା ଫାଷ୍ଟ ଏଫଟିପି କି ନା ଆଗରୁ କରିଥିଲେ?
ନାଇଁ ସାର୍, ଏଫଡିପି ଏଇଟା ଫାଷ୍ଟ।
ଏଇଟା ଫାଷ୍ଟ ଅଟଳ ଏଫଟିପି।
ଟୋଟାଲ ଏଫ୍ଟି ଏଇଟା ଫାଷ୍ଟ।
ଆଜି ଆଜି ଡେ 3 ବୋଧେ ନାଇଁ?
ହଁ ସାର୍, ଆଜି ଡେ 3।
हाँ सर
ମୁଁ ଟିକେ ଗୋଟେ ଗ୍ଲାସଟେ ପାଣି ପିଇକି ଆସୁଛି ଟିକେ।
ହଁ ସାର୍, ଆରାମସେ ଯାଇକି ଆସନ୍ତୁ।
ନାଇଁ ମୁଁ ଏଇଠି ଘରେ ଏକା ଅଛି।
ହଁ ହଁ, ଠିକ ଅଛି।
ସାର୍ ଆମରି ଫାକଲ୍ଟି ମାନେ ଜଏନ୍ କରିନାହାନ୍ତି।
କାଲି ଗୋଟେ ରିମାଇଣ୍ଡର ପଠାଅ ହେଲା ଆଣ୍ଡ
ଦେଖୁନାହାନ୍ତି ଏଇଠି ସବୁ ଆଉଟ୍ ବାଲା ସବୁ ଅଛନ୍ତି।
କାଲି ଆମେ ଡିସ୍କସ୍ କରିବା ବୋଲି ask the people to join actually nothing they must be serious on all these issues
ଏଇ
it
ତ
is
ଆମର
good that
କଣ୍ଟ୍ରାକ୍ଟର ଇଏ ଗୁଡାକ ରହୁନାହାନ୍ତି ଆଉ।
we are good that we are getting some funding to have this type of program on campus ଆଉ ଯଦି ଆମର ଏଇ ଲୋକ ଯଦି ସପୋର୍ଟ କରିବେନି କୋଅର୍ଡିନେଟ୍ ତାହେଲେ ତ ପୁଣି ପ୍ରୋବ୍ଲେମ ନା ସବୁ। Okay, anyway, sir ଆସିଗଲେ start କର ଆଉ ପ୍ରବୀର।
ହଁ ସାର୍, ହଁ ସାର୍।
Okay, because we do not ଆଉ already we 6 ମିନିଟ୍ ହେଇଗଲାଣି।
ଆରେ ଜଏନ୍ କର। ଅଛ ତୁମେ ନାଇଁ ଏଇ ବିଶ୍ୱନାଥ
ଆସିଗଲାଣି।
Sir, good evening all. I, Dr. Prabir Kumar Shetty, the co-coordinator of the atal FDP, with the theme of the architecture design strategy for signal processing algorithms using approximation techniques. Today is the third day and third session. And today the invited speaker is Professor Udgata sir from Central University, Hyderabad. So I welcome to all the participants and my faculty colleagues and the research scholar and the MTech scholar and the PG scholar to this third session and third day of the FDP. So now I request to Prabhupada to introduce Professor Udgata sir.
A very good evening to one and all present over here. I find myself very proud to welcome you all to the third session of Faculty Development Program by AICTE Training and Learning on Architecture Design Strategy for Processing Algorithms using Approximation Techniques. Today, Professor S.K.Udgata, Central University, Hyderabad, will share his experience and research on the topic human activity recognition using Wi-Fi signal and propagation. He is a professor in School of Computer Science and Information Science, University of Hyderabad. He served at the Center of Modeling, Simulation and Design as a director between 2012 to 2016. He has a master's and PhD in computer science from Berhampur University. He was a United Nations Fellow and worked in the United Nations University, International Institute of Software Technology Macau as Research Fellow in the year 2001. He is a recipient at IBM SUR Award Grant for the project Mobile Sensor Network-based Disaster Management System with special emphasis on Rescue Management System. His research focus is on intelligent algorithms for wireless communication, mobile.
Yes, sir, visible.
Yes. Let me check whether the slides are changing or not. Slides are changing also, right?
Yes, sir.
Yes,
Okay,
sir.
very good. So all set. So the title of this talk is we are working on a particular technology called WISE Tech. This WISE Tech stands for Y stands for Wi-Fi, and SE stands for sensing, and this tech stands for technology for human activity recognition. So today I will be talking about how these wireless signals can be used for sensing, and then different type of sensing, and one type of sensing is that how do we also recognize the different type of human activities like sleeping, jumping, falling down, sitting, running, and moving, walking around, waving. So these are different type of human activities and how human activity can be recognized using the wireless signals. So I work for School of Computer and Information Sciences at University of Hyderabad. University of Hyderabad is also recognized as a Institute of Eminence by Government of India. So to start with, if you look at the importance or the impact of this Wi-Fi sensing, this is a electronic design magazine, and it says that Wi-Fi sensing is going to be the next big wireless movement in the world actually. So so far, in different ways of the technological impact on the society, like the internet was a revolution. Before that, the if you look at this wheel was a important innovation. Then came so many things actually, and one of the recent innovation is the internet. After internet, it was actually the search engine, the browser. The browser make a huge impact on the science and technology. And then these days, actually, people are talking about that this Wi-Fi sensing will be the next big wireless, movement in the in the world, which will be of a various impact on different type of social and scientific applications. So, having said that, when I say that Wi-Fi sensing, it actually started as a title called sensing without sensors. So when I say sensing without sensors, I repeat, it is sensing without traditional sensors. For example, if you have a temperature sensor, the temperature sensor can measure the temperature. If you have a humidity sensor, the humidity sensor can measure the humidity. If you have a pressure sensor, the pressure sensor can measure the pressure. Similarly, here we are trying to measure the environmental parameters or different parameters without using the traditional temperature sensor or pressure sensor or humidity sensor or fire sensor, etc., etc. So so this is also called like it started as a sensing without sensors. Then people realize that we cannot call it as a sensing without sensors, because Wi-Fi devices are also sensors here. So there is a device here. Then they said that this is called device-free wireless sensing. For example, you don't have to make a separate device, including embedding the sensors into it and then do the sensing. So device-free wireless sensing, sensing without sensors, Wi-Fi sensing, RF sensing. RF means this radio frequency, right? RF sensing, etc. These are the different synonym terms that are used for this type of a technology. So this is the slide which says that there is a huge impact of this particular technology on different social and technical applications. Now, if I start talking about what is this Wi-Fi sensing, we'll also talk about the signals and all that. So this Wi-Fi sensing is a new technology that enables motion detection. Motion detection means motion detection of the human beings. It also enables gesture recognition. Gesture recognition, if you make some gestures like hand movements, your body movements, etc., it should be able to recognize that. And it is also used for biometric measurements. What is biometric measurements? For example, your body temperature measurement, your heartbeat measurement, your so there are many other biometric measures. For example, your eyelid up and down. So some of these biometrics of the human beings also can be measured using the Wi-Fi signal. So when I say Wi-Fi signal, it's a wireless signal with 2.4 gigahertz band or 5.0 gigahertz band. So according to IEEE 802.11 AC, they say that according to that standard, Wi-Fi means wireless signal at 2.4 gigahertz band. So in this case, we use the two. So if I use other band like except 2.4 gigahertz, if I use 2.5, 2.8, 3.0, etc., this is simply called as a RF signal. Now the RF signal has a different bandwidth, etc. When I talk about Wi-Fi signal, it focuses on 2.4 gigahertz. So what actually happens actually, this sensing or this technology, this motion detection, gesture recognition, etc., because when you make a gesture, you make a movement of your hand or you make a movement of your body, or so there will be the signal which is transmitted at a particular from a transmitter and received at a particular receiver, and there is some activity that is happening between this transmission and the receiver. Then the signal gets reflected, the signal gets scattered, and the signal also fades in the transmission medium, right? So there is a fading mechanism, there is a scattering mechanism, there is also a reflection mechanism, and that is why the signal characteristics changes between the transmission point to the receiver point. So what we try to do is that we try to kind of capture these changes in the pattern in the characteristics and try to map that pattern to some kind of an activity. So then our machine learning algorithm, pattern recognition algorithm, etc., takes over and try to see that if this is a pattern that can be identified with a fall, or this is a pattern that can be identified with a jump, or this is a pattern that can be identified with a sit, or this is a pattern which is identified with a increase in the temperature in the environment, or this is a pattern which resembles with decrease in or increase in the humidity of the environment. So what is that actually I'm trying to say? I'm trying to say that whenever you transmit a wave, wireless, a signal, and then receive a signal, depending on the characteristics of the medium and depending on the activities that is performed in the medium, the receiver signal will undergo certain changes. Now, if that changes can be captured properly, and if that changes can be, and if you can extract the patterns from those received signals, and then you can try to do some kind of a machine learning or pattern recognition algorithm such that you can level that particular pattern with a particular activity. And then for testing, you can always measure them. So what actually happens is that, and why it happens, look at the second bulleted point. The Wi-Fi signals are electromagnetic waves actually, and the propagation of waves depends on the dielectric constant of the medium. I repeat what I say here. All these RF signals or Wi-Fi signal means RF with 2.4 gigahertz, they are actually electromagnetic waves, EM waves. And the physics says that the propagation of the EM waves or the electromagnetic waves depend on the dielectric constant of the medium. It's not only about the medium. Suppose it passes through a wall, right? And if the wall is made of a brick and mortar, the dielectric constant of the wall is different. If the wall is a glass wall, the dielectric constant is different. If the wall is a concrete wall, the dielectric constant will be different. If the wall is a wooden wall, the dielectric constant will be different. If it passes through a human body, the dielectric constant will be different. If it passes through different liquids, the dielectric constant will be different. So when the dielectric constant changes, the electromagnetic wave propagation characteristics also changes. And that's where you can say that if you can capture that characteristics changes in the electromagnetic waves, you can map it back or you can reverse engineer it and then find out that what is the actual material or what is the actual characteristics of the medium. The last point is that Wi-Fi has become a suitable solution because of its bandwidth, because of its coverage, because of the penetration and transmission power. Now let me talk each point here. One is that the Wi-Fi has become suitable solution because of its bandwidth. Now look at this bandwidth. Bandwidth is 2.4 gigahertz or 5 gigahertz. So they are actually free bandwidth. That means the government of India is they are unlicensed band. People are not paying or the companies are not paying to use that particular band actually. So Wi-Fi is a unlicensed band. So 2.4 gigahertz is an unlicensed band and you are not paying to use that 2.4 gigahertz bandwidth. So, and this particular bandwidth is not very long range. At the same time, it is also not very short range. So it is able to cover a kind of a reasonably good area. For example, if you take a standard Wi-Fi access point, it covers around 50 feet to 100 feet, depends on the line of sight, the structure of the room, etc. So 50 feet to, almost 100 feet. It clearly covers around 100 feet actually. So 100 feet radius for one Wi-Fi access point. That means with one Wi-Fi access point, you can monitor a kind of a medium sized home or even a large sized home. So if you look at a home appliance or home scenario, in a home, I can put one Wi-Fi device and that one Wi-Fi device is good enough for that Wi-Fi signal to reach every nook and corner of that particular home. So the coverage is pretty good because you don't need unlike your GSM band or unlike your very high frequency band, etc. The Wi-Fi frequency or Wi-Fi band has a reasonably good coverage. This third point is that the penetration. All these Wi-Fi signals, I mean the 2.4 gigahertz signals, etc., they are capable of penetrating the walls. So line of sight is not an important point here. So the signal that is coming out of this Wi-Fi transmitters, they can penetrate the walls, they can penetrate the different obstacles. Of course, it depends on the type of obstacle, but still the characteristics is that it is able to penetrate the wall and still reach. So for example, if I have a Wi-Fi access point in my drawing room, I can still have access in the in the bedroom, or to some extent, if I have a Wi-Fi access point in my neighbor, I can see the signals receiving in my home also. So what does it mean? It means that it is able to penetrate the walls, it is able to penetrate the obstacles, it is able to penetrate the wooden block obstacles, etc. Why it is important? So because of these characteristics, we don't need that the device has to be in the line of sight of the activity that is being performed. The device can be in the non-line of sight. This also leads to a particular application called as a through wall sensing. What is through wall sensing? That means you are able to sense what is going on across the wall by putting your device or Wi-Fi access points or Wi-Fi transmitters outside the room. So for example, if I put my Wi-Fi transmitter outside the room, or if my Wi-Fi transmitter is inside the room, I can put my receiver outside the room, that means across the wall, and still can measure what is happening or still can measure the change in the signal pattern, and then I can find out that if there is some activity is happening within the room or not. So this is one of the important characteristics which doesn't require line of sight. It does not require lighting condition. For example, if you have to work with camera, you require proper illumination, you require proper line of sight, etc. But Wi-Fi doesn't need that. And fourth one, the most important part is that depending on the requirement, you can, of course, for military requirement, etc., because your commodity, commercially available Wi-Fi access point doesn't allow you to change the transmitting power. But for special purpose applications, the transmitting power can also be tuned, can also be changed, so that what happens, the signal character, the signal um, power, the power of this signal increases with the transmission power. So that helps us to reach to a better coverage, to penetrate, some kind of a material which is very difficult to penetrate with low transmission power. So these are basically the characteristics of the Wi-Fi sensing, which makes it suitable for different type of applications. First and foremost important thing that Wi-Fi signals are electromagnetic waves, and their characteristics change, or their propagation characteristics change, because that depends on the dielectric constant of the medium. If the and dielectric constant keeps on changing for different type of medium, for different type of bodies and all that. Secondly, that the Wi-Fi has the characteristics of coverage, penetration, tuning of the transmission power, etc. Now, because of these characteristics, we can see that the Wi-Fi signal will change its characteristics between the transmission point to the receiver point, depending on the activity, depending on the medium that is going, the transmission medium through which it is propagated. Now, if I can capture the characteristics of the changes in the transmission medium and then find out what is exactly happening, then I can find and make a database of different activities, different changes in the characteristics, and what exactly happens to the signal. Then I can always reverse engineer it and find out what is happening there. Now, this Wi-Fi is, I'm just continuing that. Let's say the first point. Now, what is wireless sensing here actually? So this I call it a wireless sensing, right? So it is a sensing event, but I'm not using any sensors. I'm using the wireless medium or the wireless signal that is being transmitted through it. So first point is that a person or object or environment within the effective area of a wireless network. So that's what I told in the previous slide, that any person doing some activity, any object present in the transmission medium or transmission area, or the environment, for example, the temperature, humidity, pressure, etc., gas, that to some extent gas, if your cooking gas leak and other things. So within the effective area of the Wi-Fi network, why I call it an effective area, within which the wireless signal is prevalent, influences the propagation of the wireless signal. I have been repeatedly telling that it will influence the propagation of the wireless signal. Now, by analyzing the wireless signal pattern and characteristics, it is possible to predict the object of the state. So, what is happening to that particular, to predict the object state means, what is that object actually, whether it is standing or sitting or sleeping or jumping or whatever. The second point is that, for example, let's say the motion sensing can be achieved by observing Wi-Fi radio signal strength and its fluctuations. So what happens when I move inside a room and my Wi-Fi signal, the receiver will detect that there is some fluctuation in the radio signal strength. So the strength will keep on increasing, decreasing, and when you move away from the receiver, there will be some kind of a fluctuation. When you come closer to the receiver, there will be some kind of a fluctuation. So what I'm trying to say that if you can see that the fluctuations, how the fluctuations are happening, then you can predict that there is some kind of a motion that is happening within the Wi-Fi zone. Similarly, however, the propagation characteristics of the wireless signals are extremely complex. We will see some of them. And these characteristics, these signals are extremely complex, and it is a challenge to develop a perfect mathematical model to extract the channel characteristics or to extract the signal characteristics from the received signal, because of so many other factors. This is all in the wireless medium, right? So there is a lot of noise that comes into picture. There are so many other wireless devices around. There are other wireless signals like your GSM signal, mobile signal, etc. So there are a lot of noise. There are a lot of other factors that adds to the complexity. And what is important for us, that how do we still able to characterize the propagation, the signal propagation, and extract what is happening there actually. Now, if you look at this actually, this Wi-Fi sensing actually, so Wi-Fi, why people, instead of RF, people are now focusing on Wi-Fi sensing. So Wi-Fi is a universally adopted standard, and as predicted by end of 2022, we are almost there actually. There will be nearly 549 million public Wi-Fi hotspots. So Cisco predicted, this is the Cisco data actually. The Cisco is a company which makes Wi-Fi access points and all that, routers. So it predicted that by end of 2022, there will be around 549 million. That means around 54.9. That means around 55 crores of Wi-Fi hotspots will be available throughout the world. That means you will find it omnipresent actually. It will be there almost everywhere. You may not see it, but it will be there almost everywhere, because 55 crores of Wi-Fi access points are supposed to be deployed in throughout the world. Now, since Wi-Fi is easily available in indoors, for example, it is available in indoors, it is also available in outdoors. So such a system could build without including much cost. So what is that I'm trying to say? The transmitters are almost everywhere there. I mean, it's almost there. In public Wi-Fi are there, indoor Wi-Fi are there, institution, you go to institutions Wi-Fi are there, you go to railway station Wi-Fi are there, you go to airport Wi-Fi is there. So almost Wi-Fi signals are prevalent everywhere. Now with your mobile phone or with your laptop or with your special purpose device, if you can receive the signal, characterize the signal, then you can characterize many of the environmental parameters that is happening around you using the Wi-Fi signals. Now, as I started at the beginning, this is called non-intrusive because you don't have to wear anything, you don't have to inject anything, you don't have to, there is no piercing effect, etc. So this is a non-intrusive. It's a device-free sensing because the devices are already there, right? I mean, the Wi-Fi transmitters are already there and they are being used for communication. Now, what we are saying, they will be also used for sensing. So this is non-intrusive device-free sensing, device-free wireless sensing, non-cooperative sensing. Why it is called non-cooperative sensing? For example, if you want that case, suppose you want to monitor the number of footsteps a particular person is taking inside the house, then what is the present technology? You are a Apple Watch or some kind of a Fitbit kind of a device, and that device will keep monitoring how many steps you are working. Now, in that case, the person or the subject or the sample has to cooperate with you to wear a watch or to wear a wearable device in the body so that you can monitor his or her movements actually. But here is a case with wireless signals. It is there in your home. The Wi-Fi access point is there. People are using it for data communication. But at the same time, the same device can be used for sensing also. And in this type of a sensing, you don't need the cooperation of your household personalities, etc. Because they need not cooperate with you because they don't have to wear anything. They don't have to do anything. They just have to do their normal activities and you should be able to monitor them. Now, compared with other state of the art techniques, such as camera based techniques, wearable sensors, for example, you have to wear a watch kind of a thing, device free wireless sensing does not require specially deployed sensing techniques. It can also work in dark and dusty environment. For example, if it is a camera, you require line of sight, you require proper illumination, you require different type of it should not be dark, it should not be dusty, etc. But whereas here is a technology with signal characteristics or signal propagation characteristics, which doesn't depend on the lighting condition, it doesn't depend on the dusty environment, it doesn't depend on your privacy and all that, it still works. Now, on what basis it works actually, as I was telling you, this IEEE 802.11n uses 2.4 or 5 gigahertz frequency band with a bandwidth of 20 to 20 or 40 megahertz. That's what it is standard actually. I mean, people might be knowing that this particular Wi-Fi protocol, it is either 802.11n and also 802.11 AC. So these are the two protocols based on the Wi-Fi signals are being propagated or being monitored or being managed. What this Wi-Fi sensing people are doing is that they are also trying to do that they will use this 2.4 or 5 gigahertz frequency band. So that's called a dual band access point. And the bandwidth is that 20 or 40 megahertz. IEEE 802.11 AC only works on 5 gigahertz with bandwidth channel of 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz. Now, this is the I don't want to focus more on this actually because when you talk about bandwidth, what happens actually, this is the 5 gigahertz, right? In the 5 gigahertz frequency, 5 gigahertz is your central frequency. Now you have multiple channels because there should be a parallel bit. The bits are being communicated in parallel. So there will be multiple channels. Channels means some small pipe kind of a thing. So there are multiple channels, and with central frequency 5 gigahertz, you will have towards left and towards right. So 5.02, 5.04, 5.06 if it is 20 megahertz. If it is 40 megahertz, it is 5.04, 5.08, 5.12 like that. If it is 80 megahertz, similarly. If it is 160 megahertz, similarly. Now, what is the difference between 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz? The number of channels will decrease, but the speed of the data transmission will increase. So, 802.11 AC works only with 5 gigahertz band with so many bandwidth possible. You can tune them to this particular bandwidth. Whereas 802.11n is a dual band. It can work either with 2.4 or with 5 gigahertz frequency. So right now in all household Wi-Fi routers or even in department centers, etc., you will find that they are mostly 802.11 and they work with only two bands, 20 or 40 megahertz band. Now, what is it? So what is that I'm talking about now? Look at the third point. The number of subcarriers. we call that as the NSC. The number of subcarriers which carry the data for wireless communication depends on the maximum bandwidth. For example, 802.11n, the tool that we have is that 30 subcarriers, and ESP32 is another controller which can give up to 64 subcarriers. Now let me take a pause and explain what is it actually. I told you, right, that 2.4 gigahertz or 5 gigahertz is the center frequency. Now this is the center frequency, and then towards the right and towards left you have so many subcarriers. So the carrier is 2.4 gigahertz, we have subcarriers. What is a subcarrier? Subcarrier is a small channel through which the data, one bit of data can transmit, or one stream of data will go. Now, how many such subcarriers are there? That depends on which protocol you are using. That depends on which NIC card. NIC means network interface card. The network interface card that you are using. For example, this 802.11n, if it is protocol, and this Intel came out with a tool. Intel came out with a NIC card called 5300N. Intel 5300N. That's the NIC card actually. So if you have Intel 5300N, which was popular, I mean, now people are not using it, but Intel 53001 was quite popular for almost a decade. Now then, in that particular NIC card, it uses 30 subcarriers. I repeat, 30 subcarriers. 30 means 30. 15 this side, 15 that side. In fact, there are some pilot signals, etc. We'll talk about that. But 30 subcarriers. And at this point of time, you just remember that there are 30 subcarriers if you use one particular NIC card. And if you use ESP32 controller, etc., it can give up to 64 subcarriers. What I mean by subcarrier? Subcarrier is a small channel through which the bits can be transmitted in parallel to the other subcarriers. So if I have 64 subcarriers, that means at one point of time, 64 bits can be transmitted in parallel. So now imagine, I have a transmitter, I have a receiver. The transmitter transmits the signal, so there is not one signal now. There are now 64 bits, 64 parallel signals are going. The receiver will also receive 64 if you are using ESP32. If you are using 30, and I mean, what is that? Intel 5300N, it will use 30. Now you get 30 30 signals. 30 signals at the receiver, and each signal passes through the medium. I repeat, each signal propagates through the medium, and any change in the medium, depending on the characteristics of the signal, the amplitude, the phase, etc., the characteristics will also change. So now I have too much of information at my receiver end, and this information I will try to parse it, I will try to extract the pattern out of it and try to recognize what is happening. Now, with this background, let's say, how do we estimate the channel? So what is a channel here? I go back to this point. I said that there is a transmitter, wireless transmitter. The transmitter transmits the signal. The receiver will receive the signal. The transmitter, the way it transmits, it follows a particular protocol. Let's say IEEE 802.11n or 802.11ac, etc. And I just gave a small brief about that which protocol uses what frequency and what bandwidth. Now in every channel, so as I told you that there are multiple channels or multiple subcarriers. So each subcarrier is a channel. Now through one channel, you transmit some bits, right? Now when the bits are transmitted, I'm not worried about the data. What the bit contains is not my contention. What is my contention is that when the bits travels to, so bit is traveling in the medium as a signal. Now when the signal comes, what happens to the signal during the transmission? So I'm not looking at any other layer. I'm not looking at MAC layer, transport layer, network layer, session layer, etc. I'm only looking at the physical layer. So in the physical layer, I hope you understand the network layers actually, OSI layers. In the physical layer, the signal will be transmitted. And in the physical layer, when the signal gets transmitted, the signal gets distorted, the signal characteristics gets changed during the transmission because of the propagation medium, because of the activities in the propagation medium, because of the changes in the characteristics of the propagation medium. And then you have to extract that, or you have to capture that in the receiver. Now, how do I capture it? I do a channel estimation. So this is what is called a channel estimation. Some of you might be knowing, and I'm not very good at that actually. So what is channel estimation here? So a signal goes through a medium, right? It's a channel, right? So as I told you that a signal goes through a particular bandwidth or a particular channel or a particular subcarrier. Now it gets distorted, or various noise is added to the signal while it goes through the channel. I have been repeatedly telling that actually when it travels through the channel is a wireless channel. It's a wireless medium. Now, because of the noise, from where the noise comes, even if you switch on your TV, right? TV is also generates some kind of electrical signals, etc. That adds to the noise. If you send some data through your mobile, then there is a mobile signal that adds to the noise. So there are so many things, right? Noise can come from any sources. It's a wireless medium. So the signal gets distorted because of the various noise that is added to the signal while it goes through the channel. It properly decodes the received signal without error. We need to remove the noises that are added by the channel. So what happens in the first part? How do I estimate the channel and why I'm estimating the channel? Because I'm estimating the channel to extract the characteristics of the channel that got distorted during the transmission. So how do I estimate the channel? I don't have anything. I have only the signal that has come through the channel. So the transmitter transmits the signal, the receiver receives the signal. Now I want to know what happened in the channel actually, or what happened in the medium. Now, yeah, to know what happened in the medium, I need to estimate the channel, or I need to get the received signal, and from the received signal, and I also know what was transmitted. So between these two, I will try to estimate what happened to the signal during the transmission. And if I can do that, then I can estimate that what is the activity or what happened to the medium actually. So the process of finding what characteristics are added to the signal by the channel is called the channel estimation. So some characteristics will change, something will be added. So the process of finding what characteristics are added to the signal by the channel is called the channel estimation. So what happened? Transmission happens, it's a pure signal. Something will be added into the signal during the transmission, and at the receiver end, you will receive the signal and try to find out what are the characteristics that have been changed or added to the signal. And this process is called the channel estimation. So the channels can, when the transmission happens, that the channel can attenuate the signal, it can shift in the phase of the signal, and it can also add noise. So these are the three things that happen during the transmission: attenuation, phase shift, and noise addition. Now the goal is to find out how much of the characteristics is added at which specific frequency and at what time. Now this is very important, and once I know this, I can find out what is happening there, and I can just map this particular characteristics to a particular event or to a particular activity. So what is our goal in the channel estimation? The goal is to find out how much of the characteristics is added or changed at which specific frequency and what time. Now what is the specific frequency? As I told you, right, 2.4 gigahertz or 5 gigahertz is my central frequency. There are many other frequencies, around 30 frequencies or 64 frequencies. These days we also get 128 frequencies, right? So 128 frequencies. So at which frequency the noise is added, that means which frequency is attenuated, which frequency phase is shifted, in which frequency the noise is added. Now the noise, these three, the channel can attenuate, phase shift, or add noise, can happen independently in each signal, because each frequency, because each frequency has a different way to attenuate, each frequency has a different way to shift the phase, and each frequency has a different way that the noise can be added to that. So I need to estimate the channel corresponding to every frequency band. Now there are many frequency bands like 64, 128 or 32, etc., depending on the NIC card you are using. NIC in the sense network interface card you are using. This is one. So at some frequency, this channel will, distort the signal, and at some time also it will distort the signal. What is the time here? For example, the transmission is happening and the receiver is receiving it. It's going on. Now suddenly I pass through the transmission medium. If I pass through the transmission medium, what happened? Because of my movement, there is a distortion in the signal, and at that time you will find that if there is some noise is added or some phase shift has happened or the signal is attenuated because a person moved within this Wi-Fi range actually. So if that is the case, so at what specific, so it might not change every frequency, it will change some frequencies, or it might impact some frequencies more and some frequencies less. And at that particular time, that means at that particular time means at what time the activity has happened. So now I can know that at this particular time this activity has happened because these frequencies changed or got distorted, because, and so you can map it there. Now, how do you do it actually? So the process of channel estimation is like this. You have a set of some mathematical models to correlate the transmitted signal and the received signal. So what you are doing, we have a transmission signal matrix, we have a received signal matrix, and there is a mathematical model to correlate them. Correlate them means the transmitted signal and the received signal, and what is the correlation between them actually. So this is called the channel matrix. Now they transmit you just transmit a known signal that is called the reference signal or pilot signal. So what happens, I mean, this is embedded or I mean coded into the protocol actually. So when the protocol IEEE 802.11n or 11ac etc., so it will first, there is a reference signal. What is a reference signal? That's called the pilot signal. So in the pilot signal there won't be any changes actually. So that's my reference signal or pure signal or whatever you call it, and detect the received signal. So first the pilot signal comes, it's like a pilot, and it's like a reference, and then and detect the received signal. So that's done. Now what happens, by comparing the transmitted signal and received signal, we can find out the elements of the channel matrix. In fact, what is our objective now is that I have to find out that channel matrix, and I will tell you how the matrix looks like. Once I find out the channel matrix consisting of the numbers, I mean real numbers. Now these real numbers keeps changing very rapidly if something happens to the channel or something happens to the transmission medium. Now if I can do that, then I can, if I can construct the channel matrix at time t0, channel matrix at time t1, channel matrix at time t2, channel matrix at time t2, then depending on the variation of the channel matrix between in the time series, I can find out what is happening in the medium during this period of time. Now, how do I estimate the channel coefficient? So the channel matrix are nothing but the channel coefficient. Now, YF, some function. Now the transmitted signal is XF. So XF is the frequency band, right? So the transmitted signal at that particular frequency is XF. Received signal at that frequency is YF. Now that F can be F1, F2, F3 up to F64 or F128. What is the channel coefficient? What is my objective? My objective is to extract the channel coefficient, that is called HF. What is H here? HF corresponds to some value of the coefficients H corresponding to frequency F. Now look at the yellow one, actually yellow highlighted area. The yellow highlighted area says that so what is YF? YF is my received signal. So YF equal to HF. HF is my channel coefficient multiplied by the vector multiplication, actually multiplied by the XF. What is XF? XF is my transmitted signal. So I have a transmitted signal that will be multiplied by the channel coefficient, and I get the received signal. What is my objective? My objective is that to find out what is HF. So the channel coefficient can be calculated as HF equal to YF, and this X bar H, X underscore H dot X underscore H is the, if you, I mean, I don't want to talk much about this, but where XHF is the Hermitian matrix of HF. So the Hermitian is actually the conjugate transpose of a matrix. So if I know what is XF, I can find out the conjugate transpose of that matrix XHF, and then XHF will be multiplied by the YF. YF is the received signal, and then you get the HF. So HF is my channel coefficient. But this is not easy. This is not easy in the sense that this works in a pure idealistic environment. There is no noise, there is no other disturbances, etc. So, and that is why, because the X contains some noise, Y contains some noise, etc., this formula exactly doesn't work. So we need to have some kind of an approximation algorithm and then decide how to extract the channel coefficients. Now, I mean, look at this slide actually. So what is the channel estimation? Again, I'm going down to this, the same channel estimation I'm continuing. So channel coefficient values are needed when there are no reference signals to find that the most common method is to interpolate measured. Okay. Don't read that actually. Now sometimes what happens, there is some Wi-Fi access point which is already there, right? And it is continuously sending signals. I was not there from the beginning actually. Now what I do, suddenly I go there and start receiving these signals. I don't have a received signal. I don't have a reference signal. I don't have a pilot signal, because the signals are continuously coming, and I intercepted the signal in the middle of this. So what happens actually, people do that they try to find out that they observe the signal for some point of time, let's say for 1 minute or 1 second or whatever time, and then take the average of that. So that average of that, they say that okay, if you take average, the noise will be kind of filtered out. So average is one such technique. There are multiple techniques to filter out the noise over a period of time, and then you extract the signal. So theoretically, you can calculate what is NF actually. NF is the noise that is there in the frequency. So YF is the received signal, and this is the YF. You subtract the H bar average of FXF. So what is this H bar of average of F? Because you don't know the reference signal, because you don't know the pilot signal, you observe the signal for some time, take the average of that, and that average you subtract it from the original signal. So that will get you the noise. Why do I say this actually? I say this because the received signal noise is not noise is not periodic actually, right? It is not periodic. So you just take out the average. And I'm saying that this is not the exact method, right? You cannot get an exact channel estimation, which is exactly, we will find out the characteristics actually. But you have to find out some way of extracting the channel characteristics or extracting the channel coefficient from the received signal. So this is directly using the formula. This becomes the formula actually. Now, what are the 4 major problems or the challenges during the digital communication? Okay, so one is that there is a okay, so there is a inter-symbol interference. Don't worry about that. When you send one packet or that's a one symbol, one data symbol, and then when it goes to one frequency, and when another data goes to another frequency, etc., there is a possibility of interference actually. With orthogonal frequencies, etc., the interference is very less, but still you cannot completely ruled out actually. So if you go for OFDM, etc., the interference is minimized, but I'm not completely ruling out the interference, and there will be some interference there. Most importantly, so this is a small problem actually, but important problems are follows. What is multipath propagation? The multipath propagation is that look at this, the transmitter or any Wi-Fi transmitter or the signal transmitter is not omnidirectional, right? It transmits in all possible directions. It's a 360 degree. It's a circular. So it's like an antenna. So antenna keeps on radiating the signals actually in omnidirectional. So in a omnidirectional antenna, the signal goes in all directions. Now let's say, suppose I'm sitting here, right, and I'm the receiver, and somebody sitting 10 meters away from it is a transmitter. Now the signal can come directly to me. The signal can go in another direction, hit the wall, gets reflected and come to me. The signal can go to another wall and gets reflected and come to me. The signal can all the way pass through me, go back, hit the wall back in my back and come back to me. So that means there is a multiple path that the signal travels before it reaches the receiver. I repeat, one signal, when the signal is received by the receiver, it is not a point signal, right? You don't send a point. This goes as a circle, this just explodes. Now when it explodes, it goes in all possible directions, and the receiver will receive the signal which is reflected from multiple paths, or which comes from multiple paths. Now when it comes from multiple path, each path adds to the noise actually, right? So how do I know that key? And there is no way that your receiver is just receiving, it's just receiving the signal, and there is no way to know that whether it has come directly or it has come through multiple path. Now multiple path will have a different level of change in characteristics, whereas direct path will have a different change in the characteristics. Of course, people have found out how to do it. Now what is co-channel interference? Co-channel interference means there is a frequency 1, there is a frequency 2, so there is a possibility of interference between these two channels. What is inter-symbol interference? When the same symbol is being transmitted in one, there is also a possibility of interference. And above all, there is a presence of noise. So noise will be always there in the channel actually. And in Wi-Fi, in wireless signals, the noise is much more compared to the wired signals. So first you have to look at the diagram below. So we call it an channel equalization. Now channel equalization is that the process of removing the ISI. ISI means inter-symbol interference, noise effects from the channel. Equalizer lies at the receiver end of the channel. I mean, we all do at the receiver end only. So at the receiver end, now look at this. The data comes, you apply some filters actually. Any filter you apply doesn't mean anything actually. You have to see which filter works better, whether it is a Hampel filter or whether it is a WDM, wave division multiplexing filter, or low pass filter, high pass filter, some filter. You try all possible filters, and this filter will get you the channel actually. So once you get the data, you apply the filter, you get the channel C corresponding to a frequency F. Now with that, you have again you add some noise actually. So what you are doing actually, if you look at this NT, the noise at that particular time, this gets added to that. Then at the receiver, you apply another filter and extract the HF. What is H? H is the channel coefficient, and then go through the equalizer and other things actually. So if you follow this path, this is a typical signal that is transmitted from the transmitter, and then it goes through the channel. Then the channel coefficients are added to that or multiplied with that. It's a vector multiplication. Then you receive it, apply the filters, and then equalize it actually. Once you equalize it actually, this will try to help you to remove the ISI and the noise effect actually to some extent. There is no method which removes everything completely. Okay. Now the equalizer is a transfer function. The transfer function of equalizer is just inverse of the transfer function of the channel actually. So what I don't know. I don't have a pen now. So let me tell you. Now let's say there is a function. There is a function. The function can be nonlinear actually. Now suppose if you use a nonlinear function that comes as an equalizer. Now how do you inverse it actually? You find out the opposite of that particular function, inverse of that particular function. Now if you multiply the inverse of that particular function with the original function, you get a straight line. You get a linear function actually. So you have a nonlinear function. Look at my hand. You have a nonlinear function. Suppose it goes as an ellipse. You try to find out the inverse of that, which goes below, and then if you superimpose these two signals, these two transfer functions, then it will find out the equalizer. It will equalize the signal, and you find a linear there actually. So equalization is an iterative process by reducing the mean square error, the difference between desired response and the output of the filters used in an equalizer. Now what they do, or what I mean by this actually, in one equalization is a process which cannot be achieved in one shot. So you require multiple shots. So it's an iterative process. You have to do it again and again. And somebody should excuse me, my knowledge in this is limited actually, but still whatever I have understood is that you have to do it repeatedly. And once you do that in a repeated manner or in a iterative manner, every time what you are trying to do, mean square error. What is mean square error? So how it is being done? First we try to simulate it in the sense that we take some signal, we generate a function generator will generate a signal. Once the signal is generated, we add noise, we add white noise, Gaussian noise, all sorts of noise, and then try to extract it, remove that, equalize it actually. Now when you equalize it, we try to find that, okay, we do some kind of an estimation and find out what is the difference between the original signal and the extracted signal. Then the difference is the error actually. Then we try to minimize the mean square error, and when we try to minimize the mean square error, so you have to do it repeatedly. That's what is an equalizer actually. So the types of equalizer, as I told you, it can be linear, it can be nonlinear also. So when you say linear, we equalize least mean square principle, we apply recursive least mean square principle. What is the least mean square principle? Least mean square principle says that you find out the error between the observed value and the estimated value, and that error you square it, because sometimes it is less, sometimes it is more. So you take the magnitude part. So that is, we square it. Once you square it, then at every, let's say there is a sampling rate of 128. So if it is 128 sampling rate, you get 128 samples. So you find out the mean of all these 128 samples. 128 is too less actually, but still. So you find the mean. Mean means average of all the 128 samples, and then this has to be minimized. You find out the d by dx of that actually, right? You do a differentiation, equate it to 0. So that will minimize the mean square error. That's a standard principle actually. I mean, people use it if you have studied numerical methods, etc. Many people have done that actually. Now what is recursive least square method actually? So just if you say it's a least square method, but you do it recursively, right? You do it recursively. Now what is normalize? Normalize says that, okay, this is very interesting. What is it? Raw data. Let's say the raw data, the signal values are 100, 200, 50, 30, 10, 2, etc. So when you try to minimize the error, sometimes what happens, if the actual value is 100 and you get 102, the error is only 2. But suppose the actual value is 2 and you get 0, the error is also 2. But imagine from 2 to 0, there is a reduction of 200%. But from 102 to 100, it's almost close. But 2 to 0 is not close. So normalize is that you normalize everything between 0 to 1, right? In a scale of 0 to 1, the values are normalized, and then they will not, the high values or very low values, they will not have an effect on the actual output. What is nonlinear equalizer? Because linear equalizers, sometimes people feel that it is not a good approximation to the actual equalization function. So people use nonlinear. Nonlinear means what? A higher order function actually. So to have a higher order function, that means higher order polynomial. If you put a higher order polynomial to this, then you use neural network, multi-layer perceptron algorithm, etc. And I suggest that you read some of these papers, etc. there. Now, in this case, I am again going to the same principle actually, the least mean square principle, recursive least mean square principle, and then maximum likelihood, machine learning methods. People have used everything actually. Now look at the diagram here. Suppose you have a X here, the X part is coming, and what is an adaptive filter? The adaptive filter is that, now look, I mean, it's self-explanatory actually. If you look at this, let me read it. What is an adaptive filter? It's a computational device. That means we design a function, a computational function that attempts to model the relationship between the two signals in an iterative manner in real time. What is real time here? That means when the time progresses, the filter gets adapted to the time actually. So in an iterative manner means not at one shot, but at multiple shots. So the output is compared to the desired signal, and accordingly the parameters of the adaptive filter is varied. Hence, it is called a self-designing filter. You take any filter. A neural network can also be filter. Your wave division multiplexing can also be filter. Any filter you take. Now you give the signal X and you have to get Y, right? So the filter is that the X signal will be given. It will go through the filter and it will get Y. Now what is so once it gives you Y, what is your desired signal? My desired signal is, let's say, D. Now if and there is a difference between Y and the D, I find out the difference between Y and D, and based on the difference I change the coefficients of the filter, the parameters of the filter, so that when next time X comes, the Y will be closer to the D. That means the D minus Y will be less. So what is adaptive filter here? The adaptive filter here is that the filter coefficients gets changed with respect to time, so that the estimated signal and the desired signal, the difference will be very less. So if that is the case, then what do you do actually? We take a so once the adaptive filter, we do it in a simulator manner. Once the adaptive filter is ready, then we deploy it in the real time. And whenever I receive a signal, I apply it to the adaptive filter. The filter will filter out unwanted signals, etc. The Y what it will give is actually the close to the desired signal actually, because we have already simulated and tuned the adaptive filter parameters. I mean, I don't want to talk more about this least mean square method, etc. They're basically trying to minimize the total error and all that. So maximum likelihood is also same thing, but let me read it out actually. So maximum likelihood is that it's a method of estimating the parameters of an assumed probability distribution given some observed data. Now what it does actually, you have a signal coming out, right? Now you see that what is the distribution of this particular, the probability distribution of particular this signal actually. This can be Gaussian, this can be Poisson, this can be, there are many such distributions actually. Even if there is no distribution, you try to fit a distribution curve. It can be normal also. You try to fit a distribution curve that this is my assumed probability and this is the parameters actually. So given some observed data, so in this case our observed data will be the signal. So in the signal I will try to distribute that what is the probability distribution of the amplitude, what is the probability distribution of the phase. So these are the probability distribution. Now this is achieved by maximizing the likelihood function, so that under the assumed statistical model the observed signal or data is most probable. Okay, let me talk in kind of a plain English. What do you have? We have a signal, or that is what is the data. We have a signal, and then we try to fit a probability distribution to this signal that is coming out actually in a simulated environment. Once the distribution is fitted, right, then what I do, so the statistical model is already observed actually. Now when I get the actual signal, right, distorted signal, etc., I know that it should follow this statistical model. Any violation to the statistical model is ignored or is subtracted. So then what you do actually, it actually removes the noise, it actually removes the distortions and gives me the signal characteristics only. It doesn't give me the noise characteristics. So the point in the parameter space that maximizes the likelihood function is called the maximum likelihood estimate. So these are all statistical parameters. The maximum likelihood estimate, or most likely it is called as MLE. So MLE tries to fit a distribution function to the signal characteristics like amplitude, phase, etc., etc. And then whenever the noise is, so once the maximum likelihood of your, what do you call, your amplitude, your phase, your other things are fixed, then when the signal comes with an addition in the noise in that, actually your maximum likelihood function will find that, and the noise is an extra. So I will go up to that point wherever it says that it is a likelihood that you are at this point, other things I will remove it actually. So that is what is a maximum likelihood estimation. Similarly, recursive least square estimation, I have already told you. Recursive least square estimation actually depends on two factors. One is called the signal, SNR, that is called the signal to noise ratio, and another is called the BER, that means bit error rate. Now, what is signal to noise ratio? Signal to noise ratio means what is the power of the actual signal and what is the noise power. Now, usually the noise power should be less than the signal, and signal is supposed to be periodic, whereas noise is not periodic, it's completely aperiodic, it's completely random. So SNR is normally represented in a log scale, logarithmic scale actually. But without logarithmic scale also, you can say that what is signal to noise ratio? Signal to noise ratio is that what is the signal strength, what is the noise strength. If the noise strength is less, then the signal to noise ratio will be more. If the noise strength is more, then the signal to noise ratio will be less. Now, because it is represented in log scale, we say minus 20 dB, minus 30 dB, minus 40 dB, etc. Now, this is one parameter, but the other parameter is also called the bit error rate. What is bit error rate? That means if you transmit n bits, what is the number of errors in the ne? So that means ne means, suppose I transmit 100 bits. Now 100 out of 100 bits, let's say 10 bits gets error. So 10 divided by 100, that means bit error rate is 0.1. So these are the two factors that are considered, and we try to minimize this, because I know that what is the bit error rate, I will estimate bit error rate, I will estimate a SNR value, and based on that my least square estimation will recursively calculate it, so that it extract the signal out of the it extract the signal out of the noisy signal. What is Monte Carlo sampling? All these things I'm trying to tell you that because we have to do some kind of a simulation to know the actual signal, and then when the actual signal comes, it helps. Those models will help me to extract it out, to find out the characteristics. One of the method is called the Monte Carlo sampling. The Monte Carlo sampling is basically the random sampling, right? You keep randomly generating samples and then train your model actually. So Monte Carlo technique it's a technique for sampling. So what is it? It's a technique for sampling from a probability distribution and using those samples to approximate desired quantity. So in simple words, it uses randomness to estimate the deterministic quantity of interest. Again, I'm telling you, I have a probability distribution. Now I know that okay, the signal, the noise follows a normal distribution. If the noise follows a normal distribution, then I keep generating random signals and add the noise in such a way that over a long period of time it follows the normal distribution. Then I get a signal with noise following normal distribution. Then this signal, I mean, it's a random generation, right? That is fed to the filter, to the adaptive filter, or to the channel estimator, so that the channel estimator gets trained, knows how to extract it using least square approximation or recursive least square approximation, or to some extent machine learning approximations using machine learning algorithms, neural network algorithms, etc. Once your model is ready, then we actually deploy it in the actual scenario, and then we say that okay, whenever this signal comes, we'll sample it out and then find out that okay, what is we'll extract the noise. So if you close your eyes and imagine the whole story, the story says that all these noise elimination, interference elimination, and all these things are still approximate and they are not 100% true. So people are still working with, and I just saw, I didn't have this in this slide, but I just saw that there is a very recent paper about this which uses deep learning methods. I mean, if some of you might be knowing about deep learning methods for extracting noise or for channel estimation. So why extracting the noise is very important, because once you extract the noise, filter it out, the noise part actually, rest of the things is very easy, right? YF equal to XF multiplied by HF. So every channel will have YF is the signal, received signal at frequency F, XF is the transmitted signal at frequency F, HF is the channel coefficient. So I have to find out the HF, so I multiply Y with X bar F. So X bar X is the transpose conjugate transpose of that particular XF. So if I know all these things, that becomes very easy. But then the signal characteristics of the pure signal characteristics of the XF is not known because of the noise characteristics, etc., etc. So for that, people use different type of simulations, different type of additive noise, different type of distributive noise. For example, normal distribution, Poisson distribution, Gaussian distribution, Weiss noise, and all these things they do in the simulation. And based on the actual characteristics, they deploy the right kind of filter there. Okay, so this is I think Monte Carlo Markov chain also. Markov chain, you know, right? Simply saying Markov chain can be thought of as a given state of particular steps. We can decide the next step by seeing the probability distribution of the states. Okay, what is it actually? Don't worry about that. What is a Markov process or a Markov chain? Markov chain is a chain of, or a sequence of events, sequence of data, where the next data can be predicted based on the previous data. How do I do that? Now, if I have let's say I have some thousands of samples, the history of thousands of samples, then the history of thousands of history means past. History of thousands of samples gives me a probability distribution. Probability distribution means how the data was behaving in the past. So I get a distribution of that. Based on that probability distribution, I can predict what is going to happen in the next data. So that is called as a Markov chain. Now to that Markov chain, so Markov chain will give me the signal characteristics. Monte Carlo will give me the random characteristics. So I add these two. The Monte Carlo, some random thing comes up. Markov chain, there is a mathematical way of calculating what is the next. These two together. So this is MCMC, right? Monte Carlo Markov chain. MCMC method has a class of algorithms for sampling from probability distribution. Now by constructing Markov chain that has desired distribution as its equilibrium distribution, we can get this sample of desired distribution by recorded status of the chain. So this is not very difficult in the sense that if you have, and I tell you all these things, the processes, the functions of Markov chain, the functions of Monte Carlo, the functions of signal generator, all these things are there. I have to do this mix and match so that my filters, my channel equalizers, my channel estimation algorithm is able to extract the channel coefficients. I repeat, the moment I'm able to extract the channel coefficients and extract the channel coefficients in a proper way, in a rightful way manner, then my rest of the job becomes little easier. But as long as I'm not able to extract the channel coefficients in a proper way, then I will not be able to build my system based on that actually. So all these things are actually working pretty well, and people have worked on this. So this is the, I mean, I just wanted to tell you the preliminaries behind this. Behind this Wi-Fi sensing is that the signal characteristics behind this Wi-Fi sensing is that I have a transmitter, wireless signal transmitter, which is the access point or the router. I have a receiver, which is my mobile phone or laptop or desktop or whatever. Now there is a receiver, there is a transmitter. I can transmit it using some other device, or I can use a commodity Wi-Fi access point which is already there. Now when the signal comes to me, it gets distorted, it gets changed, the characteristics gets changed because of the noise, because of the change in the characteristics of the medium, etc. Now at the receiver end, I have to estimate the channel to extract the channel coefficients. Now once I extract the channel coefficients, then I will build a system based on that, because the channel coefficients will keep changing whenever there is a change in the channel propagation medium. To extract the channel coefficients properly, I follow all these methods. I follow least mean square error method. I follow recursive least mean square error method. People have started using deep learning for that. People have used different simulation techniques like Monte Carlo techniques, Markov chain techniques, Monte Carlo Markov chain techniques, etc., etc. Now, once you have this, with this background, so what is this now? Now let's say that I have a transmitter, I have a receiver. The receiver is equipped with all the channel estimators, channel estimation algorithm. So whenever I receive this signal, I estimate the channel coefficients. Now these channel coefficients are known as the channel state information, CSI, channel state information. Not so when I say it is channel state information, so I get a channel state information corresponding to every frequency band. I repeat, corresponding to every frequency band. So that means what? If I'm transmitting the data at 2.4 gigahertz, that's the center frequency. I have many subcarriers. Now, depending on the type of NIC card or network interface card you are using, you can, and the IEEE protocol you are using, you can have many subcarriers, 32 subcarriers, 64 subcarriers, 128 subcarriers, 256 subcarriers. So you have different number of frequencies through which the data comes, and you can estimate each channel. I repeat, you can estimate each channel or each subcarrier for the channel coefficient. Now the channel, once you get the channel coefficient, you get the channel state information. Now those channel state informations keep changing when the medium, the transmission medium characteristics changes. Now this is what, based on that, and how the propagation characteristic will change, because the channel has the propagation medium has a dielectric constant. The propagation medium can reflect signals, the propagation medium can scatter signals, the propagation medium can fade the signals. All these effects are all these cumulative effect will be there in the received signal or in the channel coefficients. Now if I can read the channel coefficients through a glass or through a lens and magnify it, then I can see, I can extract some patterns. Based on those patterns, I can match what is happening in that medium. So how the sensing can be done? Now at least one Wi-Fi transmitter and one Wi-Fi receiver should be there, needed for the sensing. At least one. Without a transmitter, without a receiver, you can't do anything. The receiver should be able to sense the changes in the transmitter signal. What does it mean? It means, I mean, the last 5 slides. The receiver should be able to sense the changes in the transmitted signal means the receiver should be able to extract the channel or estimate the channel coefficients and extract the channel state informations from the transmitted signal. Now initially the system learns from the environment with no humans in it. Now how does it work actually? So first what you do, let's say I want to detect human activity. So first I put a transmitter, I put a receiver, and there is nothing there actually in the room. It's a pure clean and no activity, nothing, no disturbance, nothing is there. It's a completely closed. Now you transmit signals, the receiver will receive signals. There is very less noise, there is no activity, there is no change in the environment, so it is clean. So that is considered the reference signal or the pilot mode here. Now, after that, whenever the system wants to track or sense the humans in that, the transmitter sends the signal to the receiver. Now, what happens? Suppose I go to in my office, there is a transmitter, there is a receiver, and there is nobody in the office. It's a clean room, etc. The transmitter sends the signal, the receiver receives the signal, extract the channel coefficients, uh, to create a channel state information table, and then stores it. Now, the moment I enter into my office, there is a fluctuation in the signal. What is that fluctuation in the signal? The signals can go up, down, etc. Now, when there is a fluctuation of the signal, now if I enter, because of my body structure, because of my height, because of my gait pattern or walking pattern, etc., the fluctuation will be different. And I tell you, if you enter or somebody else enters into the system, let's say a baby enters into my office, then because of its height, its body structure, etc., the fluctuation in the signal or the channel state informations or channel coefficients will be different. Now, because it is different for me, different for the baby, different for somebody else, then looking at this, and if you can train it properly, looking at the signal fluctuation, you can tell who has entered into my office. Now look here, I don't have a camera, I don't have any other device. It's just only the Wi-Fi transmitter that is there in the office. So the receiver receives all the refracted signals from the object and humans along with the transmitted signal from the transmitter. That's what it does. Then what happens? So this is what I have been telling you actually. So the OFDM, orthogonal frequency division multiplexed, OFDM signals are used as the multiplexing technique, which provides digital multi-carrier propagation. Now what happens actually, there is a and if you look at it, let me look at the diagram actually here. Now there are 1 to n number of subcarriers. So there is a multiple sub channel or the subcarrier provided parallel transmission. So you have this side, left side is the transmitter, right side the propagation medium there. Now the transmitter converts that particular data or the communication packet into n number of subcarriers and then transmit them in parallelly. Now at the receiver end, all these parallel signals or the parallel channels will be received, and for corresponding to each subcarrier, it will extract the channel state information or it will estimate the channel coefficients. So AFDM divide the signal modulated with FSK, PSK, QAM across multiple subcarriers occupying a specific channel. That I have been telling you. If its center frequency is 2.4, if the bandwidth is 0.2, then 2.4, 2.42, 2.44, 2.46, etc. Similarly, on the left hand side, it will 2.38, 2.36, 2.34, etc. So it will, and then you have frequency shift keying, PSK, phase shift, frequency shift, QM, and all these things will be done. And the modulated signal will go through it. So I'm not worried about the signal characteristics. But why I'm looking at the modulation also? Because for different modulations, the characteristics will be different. I mean, the channel coefficients will be different. So I need to know what kind of modulation is being used, so that with corresponding to that modulation, I will find out what are the channel coefficients or what are the CSI values. Now the subcarriers undergo multipath effect. I told you what is a multipath effect, because it gets reflected from different walls, etc., and then reaches the receiver at different point of time. So the subcarriers undergo multipath effect due to reflections, absorption or diffraction of the surface of the walls. So some walls will absorb it, some walls will kind of reflect it, some walls will diffract it. So all these things will be accumulated, and this cumulative cumulative signal characteristics will be obtained at the receiver end. Now, what is this CSI based Wi-Fi sensing? CSI means channel state information. Channel state information is nothing but the matrix that comes out of the channel coefficient. Once you estimate the channel coefficients, you can get the channel state information. Now look at the left side figure actually. So look at the fluctuations actually. I mean, it just looks like a fluctuation. It actually, if you plot the channel state information values, they look like this. What are these rows? The rows are each signal, each subcarrier. Let's say the first row is first subcarrier, second row is second subcarrier, third row is third subcarrier. Let's say the last row is 64. So there are 64 subcarriers. Now in the 64 subcarriers, the values are there actually, the channel coefficients are there, and they are They are kind of the pattern, you can see that they are changing actually. So when they change it at some point of time, look at the how do I say, if you can see my cursor, if you can see my cursor here, now look at this. At some point of time, you can see that there is a sudden fluctuation in the channel state information actually. That points to some activity there actually. Maybe somebody has entered, or maybe somebody has gone out of the room or something. So, but I cannot say anything about this just looking at this, because they have to be completely trained. They have to be completely tested before they are deployed actually. So the left side figure, if you plot the channel state information or the channel coefficients corresponding to every subcarrier, it looks like this. The fluctuations are also there because the fluctuations is an indication of something that is happening. I don't know exactly what is happening, but something is happening. So let me read out the sentences here. So channel state information is a physical layer information. I repeat, it's a physical layer information. It's nothing to do with the network layer, transport layer, etc., etc. So CSI, channel state information, is used to capture fine-grained variation in the wireless channel. What is a fine-grained variation? Any small changes in the medium that will be captured in the channel state information. You know, there is another thing also. I will talk about that also. There is a called RSSI. What is RSSI? RSSI stands for Received Signal Strength Information. So what is the received signal strength? Received signal strength indicator in that case, suppose the transmitter is sending a signal with a strength of, let's say, 1. Now when you receive it at the receiver end, the received signal strength may be 0.9, 0.8 or 0.6. Now that means what? Depending on the distance, depending on the medium, depending on the characteristics of the medium, depending on the number of people present in the medium, because they will absorb some of the signals, etc. So for example, in a empty room, you transmit the signal at, let's say, power P, and at the receiver you receive the power with power R. Now let's say you transmit the signal at power P, you receive the signal at strength R1. Now that's an empty room. Now if there are some people inside the room, then that R1 becomes R2, and R2 is a little less than R1 because some human bodies will absorb the signal. So that is called RSSI, Received Signal Strength Indicator. So what is the RSSI value? You can just imagine that in your mobile phone you see some bars, right? That is your signal strength. That signal strength is nothing but received signal strength. Your mobile tower is sending the signal and you receive the signal, and your strength is represented as vertical bars actually, 3 bars, 4 bars, 5 bars, etc. And these 3, 4, 5 bars are nothing but the received signal strength. They keep changing. Now I repeat, now you can imagine that you sit at the same place, but the received signal strength changes with respect to time. Because of what? Because of some movements, because of some cloudy weather, because of some, even if the aeroplane passes or buses passes, car passes, you will see that the received signal strength changes in your phone. Now that is only one parameter, whereas CSI is a multi-parameter, huge number of values you get, and any small changes in the environment or activity or sensing will reflect the CSI value. So CSI is the strength of individual subcarrier. What is an individual subcarrier? There are many subcarriers. So one CSI value corresponds to one subcarrier. It contains the amplitude and the phase measurement of each OFDM subcarrier. Now, this is much more informative than RSSI. What is RSSI? RSSI is the total, only one value. Now, whereas CSI gives me per subcarrier. If there are 64 subcarriers, it will give me 64 values. Now, in each 64 value, the CSI value is actually a complex number. Complex number means there is a real part and there is an imaginary part. The real part is the amplitude part and the imaginary part is the phase part. So the CSI value that you get, or the channel estimated value you get, the channel estimation value you get is a complex number. That complex number can be passed to find out the amplitude and phase. So what happens now, if there are 64 subcarriers or 128 subcarriers or 256 subcarriers or even 30 subcarriers, for each subcarrier you get a CSI value. Now CSI value, for each CSI value there are two parts, amplitude part and phase part. Amplitude is the strength of the signal, phase is the angle, right? So when the signal is propagated, at what angle it is propagated and at what strength it is propagated, right? So you extract the amplitude and the phase. So if there are 64 subcarriers, 64 into 2, 128 values you get per subcarrier. Now if there are, sorry, 60 per frame. So if one bit comes in the channel, per bit one signal comes, that means one data comes per bit. What do you get? You get 64 subcarriers. So 64 means 64 into 2, 128 data items. That means 64 amplitudes, 64 phases you got per frame. That means when one frame is transmitted in the wireless medium and it is received by a receiver, you get 128 numbers, and Out of that, 64 are amplitude and 64 are phase. Now what happens? If you get another frame, you get another 64, sorry, another 128, you get another frame, you get another 128. So, and you remember they're 100 mbps, and all this, the sampling rate is very high. So what happens is that if you observe the system even for 5 seconds, you get around 100. I'm saying the minimum. If you observe the system for 5 seconds, you get around 100 frames, 100 packets. Now 100 frames, each frame consisting of 64 subcarriers, each subcarrier consisting of two numbers. So 100 into 128 number of amount of data you get per 5 seconds. So if you observe the system, you just observe the receiver for 5 seconds, you get these many numbers. So within the 5 seconds, if some activity happens, these numbers, this 128 to 100, right? 12800. This 12800 values will change somewhere. Now, if you can see the pattern, as a heat map, if you can see the pattern, then you can map it to, or you can level it as some activity. Whereas, so this is what is the total value of the CSI. Whereas what is RSSI? RSSI only gives one value. Per frame, it gives one value. So if you have in the 5 seconds, if you get 100 frames, you get 100 values. Whereas in CSI, you get 12800, those many number of values. So CSI is more fine-grained compared to RSSI. Now, the main challenge in CSI-based approach is the accessing the CSI data on commercial devices is difficult, and they keep the CSI private features. Now, okay, what does it mean? It means that unless you do a channel estimation on your own, unless you do the channel coefficient extraction on your own, the commercially available your transmitters and receivers, they don't give you any access to the CSI approach. However, having said that, now Wi-Fi 5 was there. Wi-Fi 6 is the current version. Current version is Wi-Fi 6 protocols. Now in Wi-Fi 7 protocol, people have realized that it has not yet come to the market, but the protocol is already released. In Wi-Fi 7, people have realized the importance of the CSI values and its applications. So now the companies are saying that in Wi-Fi 7 protocol, the users will have access to the CSI information. They don't have to write the code for channel estimation, etc. The channel estimation will be done by the receiver. They will have some kind of functions here, and the user will have access to the CSI data directly, but that too in Wi-Fi 7 protocol. As of now, it is not there. So this is a challenge actually. In fact, it took us almost 1 year to extract the CSI values from the received signals, because there were a lot of challenges in the coding actually. But once you are done with that, and now also I'm telling you, because the kind of CSI values you extract, because they are all approximate, they are all error prone, they all differ when the noises are differing and all these things. So there is always a better method, or there is always a chance for improvement for extracting the right kind of CSI values. And if you have a right kind of CSI values, you will have a right kind of predictions. You have a right kind of sensing actually. So with the help of CSI techniques, we can do more accurate localization, object tracking, interference evaluation, and all that stuff. So what is this flowchart for Wi-Fi sensing so far? How does it work? Look at from left to right. So what is my input? My input is that there is a, if you look at this left and bottom figure, left bottom figure, there is a Wi-Fi signal here actually. So this Wi-Fi signal is a transmitter actually. It keeps transmitting. So there is a furniture in the room. There are some people who are there in the room. So it gets, and these are the desktop, mobile, laptop, etc. They are the receivers. So the receivers will receive the signal that is transmitted from the Wi-Fi transmitter and gets reflected by the human body, by the furnitures, etc. And then the receiver will extract the channel state information after doing the channel estimation. So what is input? What is my input to the system or input to the program? The input to the program is the channel state information. So what is the channel state information? If I observe, as I told you, if I observe the system or if I observe the receiver, or if I receive the signal for at least 5 seconds, I get so much of information actually. Now if I observe the system for 1 hour, huge amount of information. So this information is now going to the next level. Now, what is the next level? Next level is the signal processing. So what is the signal processing? Even you get the channel state information, lot of noises are already there actually, even if you filter it out, etc. So people use the signal processing algorithm for noise reduction, then transforming the signal from one form to the another form. They use FFT, they use IFFT, they use all these things actually, from time domain to frequency domain to time domain, etc. Because different applications require different type of transformation, and then you extract the signal. So first what you do, we have a channel state information. The channel state information is processed to the signal digital DSP algorithms. The DSP algorithms are nothing but the noise reduction, signal transformation, signal extraction, standard algorithms. We have not done anything else. Then you come to the algorithmic part actually. Now, what is the algorithmic part? The algorithmic part is that you try to model this. What is the model here? The model here is that now look at this. I conduct hundreds of experiments, thousands of experiments. I put a transmitter, I put a receiver. I ask my students to do different type of activities and collect the data for 5 seconds, level it. Now, once you level it, that this is the CSI value corresponding to jumping. This is the CSI value corresponding to long jump. This is the CSI value corresponding to very short jump. This is the CSI value for sitting. This is the CSI value for sleeping. This is the CSI value for jumping, falling down. So, and I do this experiments repeatedly and collect huge amount of data and level them. Once you level them, then people can understand that you can build a machine learning based model. So the learning based model or modeling based model, etc. And some people use hybrid model also. So when I say model based, I say supervised model, unsupervised model, semi-supervised model, etc. So all the data will be leveled and some can be unleveled also, so that I can do a semi-supervised model. Now, once the algorithms are ready, so then look at this. I conducted the experiment, collected the CSI values, did the channel estimation, collected the CSI values, then moved to the signal processing algorithms, then moved to the machine learning or intelligent algorithms that AI and ML comes out. Now, what are the applications? The application is that there are 3 types of application. One is that first to detect that something has happened, right? How do you detect? The moment you see that there is a deviation in the pattern, a major deviation in the pattern, etc., because you don't have to run the model every time. So first part of the application is that detect that something is happening. Some let's say a fire occurred in your home, right? So when the fire occurs, actually the temperature, humidity, etc. changes. Now when the temperature, humidity changes, the amplitude, phase, etc., because the dielectric constant will change and then propagation characteristics will change. Once it changes, you can see that something has happened. Now, the moment something has happened, then your models, the algorithms that are already trained, they come into picture and they try to recognize what has happened, whether somebody has fallen down, whether somebody is jumping, whether there is a fire in your house, etc. So that's the recognition. And after that, you can also estimate what is going to happen, because if there is a fire, you can do some kind of estimation and all that. Right. Now, this is another diagram which says that again, it's almost similar thing, but I will tell you what is the difference between these two. So this is the flowchart for the Wi-Fi sensing with signal processing. And then here you see the almost same thing actually. So there is there is a, look at my cursor here. There is a transmitter here, there is a receiver here, and there is a some kind of a ground truth actually, right? Some user is sitting here. There is a B is a person actually. A is a person, B is a person. So there are 2 persons. One person is sitting here, another person is sitting here. There is a wall here. Now the transmitter sends the data, sends a signal. It can go directly via A to R. It can go towards the wall and get reflected. It can come towards B and get reflected, and there are so many other things. Now the A, let's say the person B is as such, but A can move towards north or towards south. Now, what is the mechanism? What is the sensing? So this is the sensing experiment. What is the sensing environment? The environment can be the transmitter and receiver can be in the line of the sight. They can be in the null line of sight. Null line of sight means transmitter and receiver, they are not able to see each other. The person who is doing activity may be in the line of sight, may not be in the line of the sight. Now, so that is one mechanism. What is the location? Yeah, what is location? The location is that where is this person actually? Whether he is closer to the receiver, whether he is far from the closer to the transmitter, whether he is in the middle of the transmitter and the receiver, whether he is at an angle of 40 degree or 45 degree from the transmitter to receiver. So we can conduct the experiments at different points, at different location points. So that's a location. Now, what is the material of that particular wall, that particular environment actually? It can be wooden material, it can be steel, it can be glass, it can be anything. For example, you are in a computer lab, there are glass walls actually, right? So these are the environment will be, the walls can be wooden, the walls can be glass, the walls can be concrete, the location can be towards the nearer to the wall, farther from the wall, middle of the room, etc. And the transmitter and receiver can be in the line of sight, may not be in the line of sight. So this is the environment part. Then what do you do actually, as I told you in the last part, first, if you want to detect the human activity, first you have to detect that there is a human being, there is a movement of the human. So that's the presence. So first to detect the presence. After you detect the presence, then the actual models come into play and they detect where is it. That means whether it is towards the wall, whether it is nearer to the transmitter, whether it is nearer to the receiver, where is it actually, that location. And then what is it doing, the behavior, whether he is walking, whether he is sitting, whether he is jumping, whether he is waving, whether he is eating, whatever it is. So what do you do actually? First, we conduct the experiment, and then in which environment actually, because when the environment changes, your sensing also changes, right? So when you do these experiments, when you collect the data, we collect the data in a very enormous manner in very different type of sensing environment, in very different type of human beings, like as I told you, a tall man, short man, fat man, woman, man, kid, etc., etc. And then the sensing is also of three parts. One, you detect that there is a presence. Two, you detect that there is where, and then detect what is it. So these are the things actually. Now I will just talk about some of the uh, actual experiments that we have done. One, like as I told you, right, this is Wise Tech. So under that, we have a project called Wise Home. So what is Wise Home? Wise Home is Wi-Fi sensing environment for smart home applications. Now it's like a smart home, whatever characteristics of the smart home it should have, but it doesn't have sensors, IoT devices, etc., etc. We are trying to see that what are the sensor-based home monitoring, smart home monitoring can be transformed for Wi-Fi based smart home monitoring. So all activities cannot be monitored, but many activities which are monitored using IoT devices or sensor devices can be replaced by a Wi-Fi based home monitoring. So instead of calling smart home, this is a smart home applications, but smart home without using traditional sensors and IoT devices, we call it a smart home using Wi-Fi sensing based. So it's a Wi-Fi sensing environment for smart home applications. Now, if you look at what is the rationality behind and this, etc. So the rationality behind, in fact, this is a funded project actually. So we had to find what is the rationality, etc. So here, what we are trying to see, if you look at the, look at the pictures here. One picture says that some old people, they are sitting in an old age home, etc. They are not able to sleep properly, or what are they doing, etc. So, and mostly they live alone. There are not many people who are around, or they have to be monitored by camera and all these things, right? So that is one scenario. The other scenario is that where if where somebody is in a restroom or a toilet or in a bathroom, etc., and they slip and fall down actually. Now here, if your Wi-Fi sensing environment can detect that somebody has fallen down inside the toilet, and remember, we cannot put a camera or something like that in a toilet, so it has to be done in a non-invasive, non-line of sight, privacy preserved manner actually. So these are the two scenarios where the old people or the senior citizens need to be monitored, and this smart home or the wise home project is only aimed at that actually. So what is the rationale here? The senior citizen population is increasing, and it will be around, considered to be around 20% by 2050. United Nations has identified health and wellness as one of the sustainable development goal, and under that, assistive healthcare. This is the terminology actually. Assistive healthcare means how do you assist in the healthcare devices, or how technology can assist in the healthcare devices. Now, everybody knows that with the nuclear family and changes in the societal norm, there is going to be a pressure on the healthcare system to provide timely and preventive healthcare to elderly person, because there are nobody to take care of them and all these things, right? Everybody goes to office and all that. So but they have to be monitored 24/7, and healthcare providers, they find it very difficult to provide preventive healthcare. That is very important actually. So a continuous monitoring of the home environment, including the regular activities, will help healthcare providers to take preventive actions and avoid hospitalization. So what is that rationale behind this particular project is that if you look at homes where senior citizens are living, they are required to be monitored 24/7 in a non-invasive, non-cooperative. So if you ask them to wear a device, etc., the moment you go, they will take it out and put it somewhere else. So they have to be, they will not, they normally don't cooperate actually. So it has to be non-cooperative, it has to be non-invasive, and it has to be 24/7 and not very cost effective. I mean, not very costly actually, right? So and then you can say that, look, you are telling that for 5 seconds you get so much of data. Look, I take a chunk of a group of 5 seconds data. If within this 5 seconds, if nothing has happened, I just ignore it. So I take a window of 5 seconds or 10 seconds or 15 seconds or 20 seconds. I observe that window if any activity has happened. If it has not happened, I ignore that window and move to some other window, next window actually. So what is the state of the art that is so far is prevailing, or as of now it is prevailing in the smart home monitoring, that key, they are all sensor based systems actually. You require sensors, accelerometer sensor, gyroscope sensor, temperature sensor, humidity sensor, or pressure sensor, gas sensor. So many sensors are there. Using that, people try to monitor the home. And camera sensors are also there. So the examples are always there. And when you want to analyze the data, etc., they are basically cloud or server based analysis actually. So smart watch, Apple Watch, Fitbit like devices, smartphones, etc., are normally used as of now. Now, what are the major challenges? The challenges are they are not very convenient actually. I don't want to wear them 24/7. Many a times they are not acceptable, in the sense that people or senior citizens or people, even kids also, they don't accept that I have to wear something, I have to be under watch, I have to walk like this, I have to do like this. They don't do like this. In fact, I tell it as one of my favorite example. We wanted to do some work with IIT Bhubaneswar actually. So that work is that you develop a belt, the belt, kind of a belt actually, which can be wear across your stomach actually, and the belt consisting of the pressure sensors. What is this actually? This belt is designed in such a way that if a pregnant lady will wear that belt, the and if the baby moves inside the stomach actually, the pressure changes actually. So this will continuously monitor the movement pattern of the baby in the mother's womb. And how? Because the pressure, when the baby moves within the womb of the lady, then there will be different pressure patterns in the belt. And if the belt is continuously worn, then the pressure patterns you can do, and the doctors can know that whether the movement pattern of the baby in the mother's womb is normal or abnormal. But this project failed because nobody was coming forward to wear this belt with an apprehension that these are all electronic devices and it will affect my baby in the womb. It might affect also, you don't know. So perception about these devices, wearable devices, sensors, electronic devices, etc., doesn't allow it to be acceptable to the larger community of the people. Now then the other question comes that even the Wi-Fi also, people say that, but they are already there. I mean, we are not putting it an extra thing actually. They are already there. They are there for data communication, internet connectivity, etc. We can use it for something else. Affordability, we are not putting anything extra. Availability, as I told you, there are 55 crores of Wi-Fi hotspots already available, and then the numbers are growing, so it is available everywhere. Privacy, it's a privacy preserved thing because you are not using any camera or any other such devices which are considered as a breach of privacy. For example, we cannot put a camera in the bathroom, etc. So the challenge is that to develop a system which is acceptable, available, affordable, and privacy preserved. So this is the technological workflow of the voice home model. What you do, I mean, look at the bottom line. The bottom line, and I'll just zoom it a bit. Yeah. So look at this same thing. So we have a Wi-Fi router or a Wi-Fi access point on this side. Look at the cursor here. There is some human being which is there in the room, or he is doing something. So the data gets transmitted, the signal gets propagated, it gets reflected, absorbed, and all these things, faded, and all these things. Then it is received by the laptop. Once you receive it, you do the channel estimation, extract the channel coefficients, then find out the CSI values, do the filtering, signal extraction, noise filtering, etc., etc. And then finally, the raw CSI value. Raw CSI value means the actual CSI values comes here. Then what you do? You have to do some kind of a pre-processing, because there are some noise which are visible there actually. So some kind of noise removal, outlier removal, etc., can be done. Then depending on the application, people use different type of transforms like frequency time domain transform, frequency domain transform, depending on the application. Some applications requires time domain, some applications requires frequency domain. So after doing this transform, you extract the signal. Then we have this machine learning based classifiers or estimator like neural network, like SVM, like random forest, like decision tree. Hundreds of machine learning based classifiers there. So what these classifiers do actually, they will classify, they will take this signal, they will give it to a pre-trained learned model, and that model will classify the signal to one of the classes. What are the classes here? The activities. So in this example, we have taken that fall is a class, sit is a class, sleep is a class, bending down is a class, heart rate increasing is a class, and then heart rate and respiration rate we have not done much actually, but these are the things also which can be monitored. Now what happens actually in some cases, look at this. Look at this. There is the line can go through transform, signal extraction, etc. Or you can directly input that after removing the outlier pre-processing, you can directly input this to the ML based classifier, and that will also do it. Now, why I'm saying that? Because the deep learning methods, which are very recent and advanced techniques, they have their, I mean, inherent characteristics of feature extraction, etc. So we don't have to do anything. Just give the raw data. The deep learning methods are so well trained, so advanced that it will extract the noise, it will extract the features on its own, and then train and find out what is the activity or what is the class. So the class here is the activity, right? What is the activity here? Now what we do, if you look at this, so once you get this data is stored in a cloud. So why do store it in a cloud? For example, let's say in a wise home environment, there is a senior citizen who is sleeping in the in the night, and now you continuously monitor in every 10-second window. Now in every 10-second window you monitor, and then if there is some activity, you just put it on the cloud. So what happens actually, that guy will be, let's say that person will be sleeping for 1 hour, and then he gets up. The moment he gets up, you detect that the person gets up. That's the class. Then you update into the cloud that at 12 midnight the person got up. Then he moved in the then after, let's say, something movement, etc. At 12:10 again you find that he's sleeping. At 1 o'clock again you say that he's getting up. Then movement, etc. So what does it mean? Somebody, let's say a close relative or a doctor, will log on to the cloud and see that what happened yesterday night. So then the doctor can get, or the relative or the friend or the son or the daughter or somebody can see that, okay, this is the pattern of that particular person in the last night. He didn't have a good sleep. He got up 10 times. He was moving around the room, let's say for almost 1 hour. So these type of informations you can get in that particular dashboard. If you look at the dashboard on the right top right hand side, so the dashboard says that how that person's movement pattern was there in a particular night in a 12 hours window. So the technical workflow is that you collect this. So this is at the white part is at the receiver end, and once it is done, this information in that case, this inference is updated into a cloud so that others can monitor it. Okay. Now this is some interesting experiment what you have done. Now look at the left hand side. Left hand side is that I mean, this is a kind of a graphical representation of the experiment what you do. So there is a reflected. These are the. Now look at this. There is a person. There are two walls, and there is a person who is walking or doing some activity there. And there is a transmitter and there are receivers actually. So Wi-Fi devices. So they are all receivers, and you have access point. So the reflected signal comes and you receive it actually. So this is how the experiment is conducted. Now look at the right hand side. So in the right hand side, oh my God. So in the right hand side, so this is inside a lab actually. So I have an access point. This is the transmitter, and I have a receiver there. And this is the lab. I mean, if you look at this, look at the cursor here. So this is the lab inside this. So there are two walls in between the transmitter and receiver, and both the walls are concrete walls, brick walls actually. The second path is the second experiment we conducted is that the access point is outside in the corridor of the lab actually. So we have a corridor. So the access point is in the corridor. We put a receiver inside the lab, right? And the receiver is connected to the internet actually. So the activity was conducted where the receiver was there. Now look at this. The first picture is that both the transmitter and the receiver are outside the lab. There is nothing inside the lab. Activity was conducted. And in the second experiment, the access point, that means the Wi-Fi routers are in the corridor, that means outside the lab, but the receiver was inside the lab. So I put a receiver inside the lab, and people conducted the activity, and the receiver identified what was the activity and communicated uploaded to a cloud. And from the cloud, I see that what are the activities that are happening in the lab actually. So in both the cases, actually, if you look at this, both the cases it's a null line of sight, because the transmitter and receiver, they are not seeing each other. There are, in first case, there are two walls in between. In the second case, there is one wall in between actually. So, okay. Now, if you look at this, what are the observation and results? I would like to say. So we observed that each activity is behaving abnormal when compared to other activities. For example, jumping gives me a different pattern compared to sleeping. Sleeping gives me a different pattern compared to falling down. Falling down gives me a different pattern compared to just bending. So the activity of doing nothing. So that means if you there is nobody there, or there is somebody who is standing still doing nothing, is considered as the reference. Now, what are the number of data obtained? As I told you, there are 64 subcarriers because I'm using ESP32 here. Each subcarrier gives me a complex number consisting of the amplitude and the phase. So 64 into 2 is 128. And you observe the system for almost 3 to 4 or 5 seconds. And within 5 seconds, I get 100 frames. So 100 frames gives me 64 into 2 number of data. So 128,000. So this is the data points I'm getting per observation or per experiment. Now, this is I'm again saying it's a, oh my God. What happened?
Your screen is not visible now. Something went
I
wrong.
don't know how this sharing stopped. Again, let me try.
Okay, sir.
Is it visible now?
No, sir.
Ooh. क्या हो गया? I don't know. I didn't do anything, but it is not allowing me to share now. Can somebody check, please?
Prabir,
I am not able to share now.
Prabir,
No, it is not showing, sir.
No, I am not able
hello,
to share also.
Prabir. Hello. Pranab, are you hearing me?
Sir. Yes, sir. Yes,
Ah,
sir.
Prabir
Is
sir,
it now?
देखला
Now it is
sir.
okay?
Yes, yes, yes.
No. Yes,
Okay.
sir. Now it
Good,
is
good.
coming.
Now
Coming,
it is
sir.
good. Now it is good. Okay. I don't know what
Okay.
happened. Anyway, that doesn't matter actually. So if you look at this, I'll just tell you let me zoom it a bit. Yeah. So in this case, as I told you, in this case, we did some experiments of, I mean, a student doing something and then falling down actually. So here, the outside in the corridor, the router is there, and in the lab, the receiver is there. So if you look at below, I mean, okay, look at this actually. So these are the pilot prototypes actually, where one is acts as a transmitter and the other one acts as a receiver. In some cases, both acts as a receiver only because we put it at two different places. So in this case, if you, I just I took the amplitude, did some kind of, we extracted the channel coefficients and then channel state informations, then did something. And finally, I just don't want to go to the machine learning part of it actually, because this is not the focus of this FTP. So if you look at this, look at the thing actually. So the leveling is like this, that red strip is that where the person has fallen down actually, right? So, and suddenly you see a dip in the amplitude part of a particular, particular subcarriers. And so how do I do? We did everything actually. We did principal component analysis to find out which subcarrier is prominent for what type of activity, right? So we found that these are the 4 subcarriers which are prominent for the fall activity. These are the 8 subcarriers which are prominent for the jump activity, etc. So all these things are in the background, and we did PCA, we did independent component analysis, we did moving averages, we did everything. And after that, I'm just showing you that when you conduct this activity, there is a possibility that look at this. The blue is just standing region actually. Somebody just stands there, so that's the blue region. And then after standing, it falls down. In fact, we didn't fall down actually. He was carrying a kind of a pillow and then drop it. So that's a kind of a falling. And then again that he picks up that, so that they again stands up, so that's again the blue region, and then starts walking around the room actually. So if you see the pattern here, it's very clear actually. I mean, it's pretty good that the falling activity can easily be detected as far as the graph is concerned, where that particular person fell down during that particular red zone actually. So at that particular point in the x-axis actually it's the time in the sense it does actually frames, and frames we collect uh, with respect to time actually, right? So when the frames are transmitted, data frames are transmitted, you get this. But here we are not worried about the data. I don't know what is being transmitted. I don't log into that particular system, right? I just get the signals, and the signal characteristics changes, and based on the signal characteristics, I'm trying to recognize what has happened here. Now the same thing, if you look at this, the same thing we have done, but only thing is that the intensity reduced a bit, because they not bit actually reduce quite a bit, and you have to use an amplifier and all that. So same thing here also, we conducted the experiment in such a way that this person falls down, gets up, falls down, gets up, falls down, gets up, etc. So we found that whenever that person falls down or the student conducted this particular activity, we see that there is a typical change in the amplitude part, and what amplitude part correspond to which subcarrier, etc. That all pre-processing has been done. Now this is one such experiment we have done. Now then we found that this only this single antenna thing, right? I mean, you know about MIMO, I mean multiple input, multiple output kind of a thing. So this single antenna gives me only one information, and you are not able to collect any phase information, because phase information you require multiple antenna to collect the phase information. So with ESP32, it's only a single antenna which gives me a single transmitter and single receiver. Now we try to conduct almost similar experiments with multiple antenna at transmitter level and multiple antenna at the receiver level. If you look at the diagrams here, actually we have a 3 antenna transmitter, and there is a Intel 5300N NIC card which also has 3 antenna at the desktop. So we connected a Intel 5300N with 3 antennas, and we also have a transmitter with a 3 antenna router. And this PCIe, that PCIe is the slot, PCI slot. We use the PCI slot to put that Intel 5300N NIC card actually. Now, why do you want to do it? As I told you, I am not able to get all types of activity with a single transmitter antenna and single receiver antenna, because the information what I get is not that fine. So we shifted that experiment. We started conducting multiple input or multi antenna kind of a thing. So here we considered 3 transmitters antennas, 3 receiver antennas, and because it is Intel 5300N, it gives me only 30 subcarriers actually. It uses a particular protocol which uses 30 subcarriers. So instead of 64, I got 30 subcarriers, but 30 transmitter 1, receiver 1, transmitter 1, receiver 2, transmitter 1, receiver 3. Similarly, transmitter 2, receiver 1. So that pairing, so into 3 into 3. So 3 into 3, that is 9. 9 into 30 subcarriers, that is 270. 270 into 100 frames, because if you observe for 5 seconds, you get almost 100 frames. Now instead of getting 1200 samples, now I get 2700 data points. Now this 2700 data points, again it consisting of the amplitude part as well as the phase part. So we get too much of information actually per second actually. So in this case, we observe that each activity is behaving abnormal when compared to the other activities at some point of time or at a particular subcarrier. Activity doing nothing, that's what I already told you. Only difference is that there I am using single antenna as a transmitter, single antenna as a receiver. Here I am using 3 antenna transmitter and 3 antenna receiver. So now if you look at this, it's very interesting actually. We found that channel 5 means what? Subcarrier 5, and we plotted everything. I'm not saying that all the channels are almost giving some indication, but there are some channels or some carriers which are giving a significant kind of a pattern here. Now, if you look at this stream 1 means transmitter 1 and receiver 1, and this is subcarrier 5. This is, oh sorry. So this is an activity where you can see a complete pic actually. So if you look at this, these are the blue one is the red one is the standard, like you are doing nothing or just sitting. That was the red one, and the blue one is that when you suddenly wake up or suddenly jump up. So these are the things, or suddenly fall down, etc. Right? So you see a typical pattern here. Similarly, if you look at jumping, like a kid was jumping actually. In fact, the experiment was conducted by one of my lady scholar, and she had a small baby, 2-year-old, and she came to the lab and started jumping around actually. So this jumping around also we plotted it, and we see that okay, whenever the kid jumps, we see a kind of a pattern. Similarly, this is just simply walking around actually. We didn't see much, but there is a continuous fluctuation because you are just walking around in the room non-stop. So basically, what we are trying to do is, as I told you, this gives us a kind of a feature that it gives you privacy, it gives convenience, it gives acceptability. It doesn't depend on the line of sight or environmental conditions. It doesn't work, but about lot of maintenance cost, etc., can also be avoided. So that was all about the I say about the Wise Home project where we are working. We are also working on another project called the health care, not care actually, that is not RE, that is RF. RF stands for the radio frequency. Now what we have done so far is that we have used only the what is that, the 2.4 gigahertz frequency, etc. But then we thought that that is not enough for 2.4 gigahertz frequency with 3 by 3 antenna and all that is not enough for all types of monitoring and all that. So for healthcare monitoring, for example, heartbeat monitoring, etc., we require some kind of a high-end frequencies or low-end frequencies. We will have to conduct experiments. So what is this actually? This is a radio frequency based non-invasive and invisible healthcare module for assisted living. Why non-invasive is understood? Why do you call it the invisible? Actually, we don't see anything actually. It's all there actually, but then still we are able to monitor the healthcare. Now this is a small experiment which we conducted actually to measure the body temperature. In fact, that was also a success actually, and the heartbeat. So a person comes, sits in front of the router, a transmitter, and there is also a receiver, and the transmitter signal goes, hits the person, comes back. Some signals will pass through, some will come through actually. So when the heartbeat changes, right, when your chest expansion happens, chest expansion, that what is that they call expansion, contraction, and all these things. So when that happens, also there is just I didn't have that graph actually. So if you see that there is a wave actually, and the wave fluctuates. So when the fluctuation happens, there is a contraction happens, and when expansion happens, the fluctuation happens in a bit actually. So all these things, if you can record it, in fact, we used. If I want to say, we use Doppler effect also here. So you used all signal processing algorithms, all sorts of machine learning algorithms, etc. And then we also use Doppler effect to find out what is the contraction and what is the expansion. Based on that, you can measure the number of heartbeats that the person is sitting across the transmitter, and then you can measure it also. It can also the body temperature, because you know when you are suffering from fever or something, there is a temperature, and the temperature has an effect on your environment actually, closed environment actually. It radiates some sort of an energy, and then the dielectric constant changes there also. So based on that also the signal characteristics changes, although it is minimal, but still it changes. The problem with this kind of an experiment is that it cannot be done in an open space, in a crowded space, etc., because the noise becomes too much there. But in a controlled environment, within the lab environment, it just works. The same thing what we did is actually we also tried to see that whether we can do it, we can monitor somebody across the wall. I mean, this was done when there was a COVID peak and all these things. We don't want to see each other actually. So there is a glass wall, and through the glass wall also you can monitor what is happening actually. So this healthcare project actually basically talks about that how do we monitor the health status of a particular person, although it's only in a lab kind of an environment as of now, but we are still able to monitor the changes by transmitting the signal and then receiving the signal and characterizing the signal to find out what exactly is the condition of that. Not all types of health, for example, I'm not doing blood test here, but at least heartbeat, at least fever, and those things can be monitored here. There is another thing, and in fact this is working pretty well actually. There is a WiMAT actually. WiMAT stands for Wi-Fi sensing based material characterization. Now what happens, suppose something comes in our to our home, and you want to see that what is that, without opening the packet, if you want to see what is that material inside the packet, whether it is cotton, whether it is glass, whether it is some kind of a steel or something, right? So what you did, I mean, if you look at this model, the model is this. So you remember this diagram, right? Let me zoom it a bit. You remember this diagram. There is a wall here, and there is a transmitter, and there is a receiver. The station is here. Now if you just there is nothing there actually. If you just receive the signal, and if the wall characteristic changes, for example, if it is a wooden wall, the received characteristics will be different. If it is a steel wall, the received characteristics will be different. If it is a glass wall, the received characteristics will be different. And if it is a brick wall, the received characteristics is different. So that we observed actually. Now taking that as an example, now, or that as the motivation, we thought that now let's say we took a kind of an Amazon box actually. In the Amazon box, we put a glass slab. We put inside the glass slab sometimes a stone, sometimes a steel, some steel elements, sometimes sand, and sometimes cloths, and all these things. Now look at this. We have a transmitter here. We have two receivers actually. If you remember a couple of slides back, I showed you two prototypes actually. So these two prototypes we are using. One we are using at the direct one. Direct one means that is the reference, and the one is what that goes through the and all these things are kept closer to each other. They are not at a different place. So what you have, this transmitter sends a direct signal to RX2, and the transmitter sends a signal to RX1 which goes via this particular box actually. Now when the characteristics of the material inside the box changes, we find interestingly the RX1 signal characteristics are also changes. Now why do you need a RX2 here? Because of the reference actually. So the reference is air, and with reference to air we are trying to calibrate it what is RX1. And say for example, I'm not able to distinguish between polyester material, cotton material, or some other, or let's say some woolen material, woolen cloth, but we are we are able to distinguish woolen, wood, glass, and steel. So these four type of materials are completely distinguishable actually, without opening, I repeat, without opening the box actually. So if I get a let's say sealed packet from some Amazon or Flipkart or somewhere, I can just conduct this experiment and find out that what is there inside that particular box, whether it is steel or iron, whether it is clothes, or whether it is glass, or whether it is something else actually. So but we conducted the experiment with glass, stone, iron, and clothes also. I don't know how I missed it. Clothes also here. So this is one experiment that can be done using the same principle is same. Get the Wi-Fi signal, transmit it, receive it at a receiver end, extract the channel, estimate the channel, extract the channel coefficients, convert it to channel state information, do all this signal processing, etc., then do the machine learning algorithms, all sorts of machine learning algorithms, neural network, all intelligent algorithms, etc., and finally classify them. Once you classify them, the classification can be human activity, the classification can be your heartbeat, or the classification can be material, and all these things. One interesting, sorry, and I will just see. Okay, this is what an experiment actually. This through wall Wi-Fi sensing. I mean, this doesn't require a thing. If you have a Wi-Fi router, the signal will come. What is the problem here is, if you go through this, this is what is actually happening, right? But when it comes back, the whole idea is that it is buried inside the noise, because when it reflects from the wall, there is a lot of noise. The signal strength reduces quite a bit. But what people have done, I mean, this is not our work actually. I mean, this I'm quoting from somebody else's work. So what they have done, look at this actually. So what they have done in this case, they have tried to characterize the, okay, it's almost like this. The signal that they want to extract was very weak actually. So they tried to characterize the noise, and then they tried to find out what is the difference in the noise instead of difference in the signal. I'm not very sure about it. As I told you, it is not my work, but still, what they have done here is a null line of sight gesture interface. So what is it sending commands to the gestures? Now look at this. Somebody is inside a room, and in the room he is going one step forward and one step backward. So the two simple gestures actually. If it is, I just want to convey a, let's say, a bit 0 or bit 1. Now if bit 0 means I will move one step forward and then come back. Bit 1 means I will go one step backward and come back. That's what the paper says actually. So two simple gestures to represent a bit 0 and a bit 1. Now suppose I want to communicate 0101 sitting inside the room, and somebody is outside the room, and I want to communicate 0101. So what I will do, I'll move one step forward, come back. I'll move one step backward, come back. Again, I move one step forward, come back, and again move one step backward and come back. So that becomes 0101. How it is done actually? So you can combine a sequence of gesture to convey a longer message. That's what I'm doing here. So step 0 is that case step forward followed by a step backward, and bit 1 is step backward followed by a step forward. So this is how the and then they put this heat map and all these things, right? They collected it, put the heat map, etc. You can see a clear distinction actually, moving forward, coming back, and moving backward and then coming forward actually. So if you see this particular diagram, it says ki 010110. This is the signal that is giving through gesture across the wall. So this again, I'm saying this is not our work. I'm just quoting from some other paper and just tell you that this is also possible, right? So this is step forward, this is step backward, again step forward. So step forward is 0, step backward is 1. So 0, 1, 1, 0. So somebody is doing some kind of a gesture, some kind of a signal there inside the room, and people sitting outside the room or people from somewhere else, they can find out that what is happening in that particular room or what kind of signal is coming out of that particular room. So this is a small exercise. And these are the, I think I didn't put other papers also. We have now 3-4 papers on this actually. This is one is called Wi-Fi signal based through wall sensing for human presence and fault detection. I think the experiment what I've said using ESP32 module. and this is an Wi-Fi, an improved Wi-Fi sensing-based human activity detection using multi-stage deep learning model actually. So both the papers are actually, for us every paper is good, but they are relatively better. So so these papers are already published. Couple of papers are already accepted also. They will also come online soon. So thank you. I think I'm a little ahead of time, uh, but I can take some questions also. Yeah, Dr. Pravir,
Uh, sir, myself Pranav is speaking.
Pranam, okay, tell me.
Okay, sir. Thank you, sir, for the nice presentation. Now, I would like to request the participants to ask the questions or queries regarding the topic.
What I will do is I'm not able to see because I've shared my slides. I'm not able to see the chat. If somebody can read the chat, I can.
Yes, sir. Yes, sir. I am just reading the chat box. Uh, Here, Dr. Jarmun Padhi is writing my gratitude to you for the
That is
August
okay. There
presentation.
are some questions.
Okay. Sir, there is no question till now in
Sir,
the chat box. Yes.
am I audible, sir?
Yeah, yeah,
Yes, sir. Audible.
Sir, my question is like as you have just told about the like wise tech, that seems like your Li-Fi technology is the same technology are being used, the same stuff are being used in the Li-Fi technology where light fidelity the 01 patents are being taken, and the same patent are being studied and analyzed to get the gestures and whatever stops we are talking about. And
yes,
if you talk about the light fidelity and the metal substance like metal and water adding to that fluorescent materials that never get interfere, that somehow we can find out in a upper hand uh, to what this wise take what I
yeah, yeah.
just
I
gather.
got your point actually. I got your point, and thanks for raising this question actually. If you look at Li-Fi, light fidelity, and other things, you know at what frequency band they operate?
Uh, uh, so
Terahertz.
yes, yes, yes,
Yeah, terahertz. Now, if you look at terahertz and if you look at the width of this actually, terahertz frequency band has no, I mean, there is no penetration power actually. It cannot penetrate walls. So
yeah,
that
yeah,
works only on line of sight conditions. It doesn't work on line of sight conditions.
yes, 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 sir.
Yeah. So I think that basically explains this. Wi-Fi is slightly different from Wi-Fi in the sense that it doesn't. It can still work on non-line of sight conditions, and it's a different technology. It's an alternate technology.
Yes, yes. So how we can see this technology is apart from this body area network stuff, like
Yeah. In fact, as of now, people, lot of work has been done. Now you can Google and browse it. Also, lot of work has been done on human. If you can mute it, I will tell. Otherwise, yeah. So as of now, hello. Yeah.
yes, sir.
So please mute it and again you will unmute it.
Yes, yes, sir. I request the participants to ask the question, then mute the mic. Otherwise, it is creating echoes.
Yes, yes, yes. Okay. So I think what was the question? I forgot.
So my question is how we can relate the technology you have stated just to the body area network, which is predominantly known
Now
for.
I remember. Now I remember. So the answer to this is that how do I relate it to body area network? How do I relate it to your wearable devices? How do I relate to all the medical devices, etc.? They are all there. They will be there. They are not going to be replaced, etc. I repeat, this is an alternate technology when this is useful for non-cooperative sensing. I mean, non-cooperative means you don't have to wear anything. You don't have to cooperate with the sensing system because as I told you, right, one of the example is that you design a belt kind of a thing to monitor the movement of the baby in the mother's womb. That didn't work because people refused to wear it. But suppose, I repeat, suppose that activity has not been done, but suppose you are able to detect that using Wi-Fi, your home internet devices, right? Then probably it is acceptable. So this technology is slightly different from other technologies, but it can also be used for those applications where those, for example, camera based, right? Human activity detection using camera or video are a much more robust, foolproof technology, almost foolproof. But now the question comes that can you put camera everywhere? Or can you put can camera work in a dark environment? Can camera work on this environment, that environment, etc.? Or don't you think that camera is a encroachment or privacy encroachment kind of a thing? So under those circumstances, this seems to be an alternate technology, and it comes out, I mean, I tell you, it is coming out as a kind of a huge, like machine learning, right? When AI and machine learning came initially, people thought, no, 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 it's not going to work, this is only data centric. You give two data to learn something, you give five data to learn something, but it has its own limitations. But soon people realize that the machine learning is giving better result compared to certain human beings also in certain examples. So it is almost like that, it's maturing. Because and I tell you also, from computer science perspective, actually, computer science perspective, it has matured quite a lot. But I tell you again, this from the signal processing perspective, actually, it has not matured quite a lot, actually, because the CSI values what you get, or the channel coefficients what you get, are still noisy, are still far from clean, actually. So that's where a lot of problems are happening, and there is a lot of scope for people who are working on signal processing or signal filtering or etc. to work on this Wi-Fi signals and real signals, actually. So that's what. Yeah.
Hmm. I think Dr. Padi, his question is answered very clearly. Any more questions from the participants?
Hello, sir.
Yeah,
Good
please.
evening.
Good evening.
Sir, I would like to know that you told that it can be used to detect a human activity.
Yes.
But is it possible to recognize the human face by using this technology?
As of now, no, but it is possible to detect the human, which person it is.
So which person means how, like
Person means,
what?
for example, as I told you, right? I am able to, we are able to detect, but it is difficult, actually. As I told you, it depends on the shape, height, structure, etc. of that particular person, and depending on that, you can find it out. But suppose me and my brother is just 1 year different, and we are all almost of same size, etc. It's difficult to distinguish, but it can distinguish between a kid, between a dog, between a bullock, between a normal person. So this is possible. But face detection, etc., is not possible. Not possible means, as of now, it is not. I have not seen anything of that sort.
Okay, sir.
But yes, it can distinguish between human beings, animals, and other things, actually. But it's basically structure based, actually.
Okay, sir.
I,
And so
I'll,
one
I'll
more
tell you one
thing.
thing. I'll tell you one thing. I show you the. I'll just go back. I showed. I mean, this figure, you see that if you do a proper experiment, actually, with multiple antennas, with multiple receivers, etc., not with single antenna, single receiver, or a one transmitter, one receiver. People have done some experiments using multiple transmitters and multiple receivers, and look at this image, actually, I mean, that heat map. That heat maps will give you, I mean, if you can combine this heat map, I mean, overlap this heat map for continuously 8 or 10 heat map, you get a structure of a human person, actually, a person. You get a structure. So that structure will give you a kind of a shade, a kind of a shadow, right? From this shadow, I think still you can make out who is that person. You got my point?
Yes, sir.
So what I'm the picture. I think the slide is still visible. I've still said it. If you look at this
Yes.
heat maps, actually, if you do with multiple transmitter, multiple receiver, etc., people have done some experiments where these you get all these images, actually. Sometimes you get the image like a hand, sometimes you get an image of a chest, and the chest is considered to be the reference point, actually, because the chest doesn't move much, other body parts move much. So, and from there, in some time frame, you get a heat map of the face. Some time frame, you get the heat map of the hand. And then if you superimpose all these things, you get a structure of a human being, actually. If it's a human being, you get a structure of a human being. And that structure tells you that whether he's a fat person, tall person, short person, etc. And probably with some kind of a training, you can find out that, okay, who is that person?
Yes, sir. And so one more point,
Mhm.
like how much time does it take to train this system Like you told that it needs to be
Okay,
trained.
training the system takes hell lot of time, but testing doesn't take any time. It takes seconds, not even a second, less than a second. What do you have to do actually? You have to take the model means it's a trained matrix that with values actually. Take this value, multiply it, and find out what is the result. So, recognizing the activity or detecting the activity doesn't take time. But yes, for training, because you have to do hundreds of data, hundreds of experiments, collect huge amount of data, and I didn't, because this is not about machine learning. I didn't talk about that. We also used a technique called generative adversarial network, where we created data from the system which matches with these type of experiments actually, right? So I say, let's say falling down, right? I created some 20 data set, 20 false. I cannot create 20,000 false actually. Then I used generative adversarial network technology, so that from this 100 data set, I created another 500 data set, which are almost equal, similar to the 100 data set. Then I used this 600 data set to training my model. This took time. This took enough time actually. It takes days together to train. But once it is trained, the recognition doesn't take time. So we did the training using, in fact, we used a GPU system to train it actually. So you trained it, and after training, you can put that model into even a small device like Raspberry Pi or a ESP32, and then it works.
Yes, sir. Thank you, sir.
Thank you. Good.
Sir, is it detecting the color?
No.
Color are also visible spectrum, that is a portion of electromagnetic
It's
spectrum.
not working on visible spectrum, right? It is not working on
Yes,
visible spectrum.
but
Here it is not.
electromagnetic radiation, that must be maybe some radiation or reflection, refraction sort of things may be happening.
I don't
Means
know. I have
different
not
color
done.
having.
I mean, it's a good idea, but I have not done that, and I have not read any paper regarding that.
Yeah.
Sir, that
But
is a part of the hyperspectral, that type of the work.
yes.
Yes. Actually, sir, I think whatever the questions previously asked, that whether it is possible for the face recognition or not, I think it may be possible, because sir, when it is depend upon, because the recognition is depend upon the structure.
Yes.
Okay, but
Yes.
if that recognition we means target oriented. Suppose we just separate it into blocks like that. Okay,
Mhm.
suppose there is a face, so we target some of the portion of the face like that. Then it may be possible, because the heat map of the eyes, nose,
Maybe
and
possible. Maybe possible.
may be possible.
Possible.
Yes,
But if you look at this type of work, right, it's all in last 4 years, 4 years actually. So far, I have not seen that type of work, but maybe
but
possible.
it
I
should
don't
be integrated to the that means part, means some portion like that. Then we
know.
can yes, like that.
Yeah, yeah.
Then it is
What
possible.
what you are suggesting is that you can have multiple, multiple transmitter receivers
Yes,
in
sir.
a
Exactly.
close proximity,
Yes,
and
sir.
then probably you should be able to detect the face, because the
Yes.
face structure can be detected, and
Yes.
from the face structure, if you can make out, that's okay. There is no problem.
Yeah.
So
Yes, sir.
structure is perfect actually. We are able to detect the structure of that
Structure.
particular object very nicely,
Yes,
but
nice.
only if you only structure is enough, I don't. That's good. But other than that, we are not. I'm not able to detect anything as of now.
Sir, in case of the face recognition, most of the things are in the depend of the structure. That means the what is the connecting point in between the nose, eyes, and shape of the eyes and toes, like that.
Uh-huh. Good, good. It's a good
Forehead.
idea actually, but I've not done
Yes.
that actually. So I don't know.
Yes.
Maybe we have to do a lot of. We have to try with multiple transmitters, multiple receivers, with multiple transmitting power and all these things. Then we have to see. But it's a good idea. I thought it cannot be done.
Yes.
Good.
But very good presentation, sir.
Yes.
It's
Thank
a
you
good.
very much.
Yes, sir.
Uh, Sir, if there is no question, then we should conclude. Okay, any more
Can I
questions from the
discuss one
participants?
point?
Yes,
Just
sir.
one
Yes, sir.
point.
Yeah, yeah. Please.
Sir, what do you think if it can be implemented to take attendance of the students in a class?
Oh,
Is
that is
it
very difficult here. Attendance of the students of a class, even the videos are not working. Even the videos are not
yes.
working. Even the videos are not working. I'm only saying that now you see we just communicated a paper. I'm not sure what will be the fate of the paper actually, but we tried to do some experiments to find out violent activities in in a room. So, for example, two people are fighting between each other, kicking each other. The activities what I showed is that they are all sleep, stand, and other things. Now you took two people in a room, and we conducted the experiment for to detect whether they are engaged in a friendly activity or a violent activity. So friendly activity that they just shake hand, they sit coolly, and they, I mean, you know what is a friendly activity, and violent activity that they body to body contact and dhakka mukki, kicking and all that actually. That we are able to detect. Okay, there is a violent activity that is happening actually. So this I mean, this is an idea that came from a kind of a domestic violence, right? So in domestic violence it's very difficult to prove it actually. So if you have a wi-fi access point etc, and then somebody with a receiver can detect that key, and your neighbor can also detect, because you don't need any password for that, you don't need to connect, because anyway you will not be able to access the data, but you are always accessing the signal. And when you access the signal characteristics you will be able to extract. You will not be able to extract the data, and which I don't bother. What is the data that is transmission? So for example, if I have a access point in my neighbor's place or in my front door neighbor, I'm always getting the signal. And if I can characterize that signal, extract it, probably I will be able to make out what is happening there. So attendance, I'm not sure, but violent activities we have done, and we have communicated a paper also.
Okay, sir. Okay, sir. Thank you, sir.
Sir, I have a small question.
Please.
Myself, Pranav. Sir, whenever we are using the ISI band,
Mhm.
2.4 gigahertz, that is we are availing at free of cost. But
Unlicensed
whenever
band.
we are doing with the higher bandwidth like 5 gigahertz band, that must
Mhm.
be with some cost, is it?
And 5 gigahertz is also free.
Okay, that is also free.
That is also free.
Okay,
You have in your home also now. All these new routers are actually coming with dual band, 2.4 or 5 gigahertz.
okay, that
Now,
means we
so
do
for
not
example,
need
in
to
my home
go
now,
for
I'm
any
sitting.
bandwidth reservation.
No. What happens is that in 2.4 and 5 gigahertz, let me tell you the difference. In
Hmm.
2.4 gigahertz, it can go. I mean, you know that lambda, right? That
Yes,
wavelength
yes,
and all
yes,
that. When
yes.
when it becomes 5 gigahertz, actually, the lambda becomes very low.
Very small.
Very small. So then the penetration power is less. For example,
Yes,
now
yes.
when I'm doing the talk here, I'm sitting in the
Hmm.
drawing room where the access point is there. Now I'm
Hmm.
connected. My laptop is connected with 5 gigahertz,
Yes, sir. Yes.
because then the data speed and all these things are very high. But if I go to my
Hmm.
bedroom, I don't connect to 5 gigahertz. I connect to 2.4 gigahertz.
Okay, okay. Understood, sir.
Yeah.
Got it, sir. Okay, sir. Thank you, sir, for
Thank you.
nicely presenting the topic human activity recognition using Wi-Fi signal propagations. Sir, you have nicely presented the fundamentals and the deep ideas on wireless sensing network and their applications. I am very much impressed on that. Although you have told many times that you are not good in the wireless sense, means the communication part, but you have nicely presented all the communication things. Sir, you have nicely explained the IEEE protocols, IEEE 802.11 protocols with different approaches of research area and their applications. The process of channel extraction and estimation criteria you have explained very much, and those are very much informative. And that will definitely help us in implementing that ideas into our research work in other application areas. And sir, you nicely explained the concept of ISA and equalization. Although many times within that you have
Mhm.
said the same word, you do not have a very much clear idea. But
To be
still,
honest, actually,
time
I
has
don't have much idea, but still.
no, no, sir. But how much you have explained that was very much clear and very much what stick to line and very much informative. So I mentioned that one. And you also, sir, explained different algorithms that for the channel estimation and the recent advances you have explained regarding the Wi-Fi sensitivity network, very much informative, and the project you discussed as the Wise Home, that is very much impressive and very much rational. And the application of the smart healthcare application is nice, and the challenges will help us in implementing in our research work. The work you have explained in your lab is very much impressive, as those all are performed in the real-time applications, and they are continuously motivating us to do such experiments in our periphery. And lastly, I would like to, sir, request you, whenever, sir, you are coming to this Sambalpur University or somewhere near Sambalpur, you are most welcome to visit our institute, and
I always go. You don't have to ask me.
and we will be glad to interact our students with you, so that they will
Thank
also
you.
get blessings of you.
Thank you. Thank you. It's our job. Wherever I will go, I will come. I will definitely come. I don't go anywhere else actually. I go there only.
Thank you, sir. Thank you, sir.
Thank you. So thank you everybody. Have a good
Thank you,
night.
sir. Sir, namaskar.
Sir,
Namaskar.
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 Good night, sir.
Namaskar.
ଆସିଲେ
Good
sir
night.
ଦେଖା ହବ ଆପଣଙ୍କ ସାଙ୍ଗରେ
ନିଶ୍ଚୟ ଦେଖା ହବ। ନିଶ୍ଚୟ ଦେଖା ହବ।
ସାର୍।
And ଅନ୍ୟ କଲିଗ ମାନଙ୍କୁ ବି କହିଦେବେ। ରଶ୍ମି ଏମାନେ ସମସ୍ତେ ଅଛନ୍ତି ସେଠି।
ହଁ ସାର୍, ସମସ୍ତେ ଲାଇନରେ ଅଛନ୍ତି ସାର୍।
ଲାଇନରେ ଅଛନ୍ତି କି? ତ ସମସ୍ତଙ୍କୁ କହିଦେବେ। They must be doing good actually.
ଓକେ
Sir, namaskar.
ନମସ୍କାର ନମସ୍କାର।
Sir,
Good.
it is good that so many people they interacted and they ask questions, because presentation quality is always reflected through the question answering.
And thank you.
And
today
you
total
made
number of participants were at 51.
Okay,
good that
doesn't
you
matter actually.
you discuss a very live work, and very interesting. And
Yeah,
let us
I'm
see.
also quite motivated about this work actually. So I
Let us
see a
see.
lot of.
Let us see. You thrown so many problem for us. Let us see how we can go about that. Because what I am finding also, there is a lot of scope for us to contribute in this area.
Yes,
Okay,
yes,
because you have a large amount of data, and you need some amount of appropriation always. And so let us see that we also, because I am also trying to look at the closely the work, and we discuss how we can some collaboration possible on that area, particularly on signal processing.
some very interesting high impact papers have come out recently actually because it's very recent work actually. People started
Okay.
working on this.
uh, No, it is very these are time demanding problems, and it is very much required, because the Wi-Fi enable this accessing or sensing might be they're taking up these problems. Earlier there are few problems people they tried to compressive sensing.
Yes, yes,
Yeah,
yes, yes.
few problems they asked that attempted, but null line of sight access, sensing and all these things. It is very interesting.
Very
That
interesting.
that is actually giving weightage to the Wi-Fi sensing.
Yes, yes. That's the key actually. This one
Right.
line of sight and particular penetration coverage and all these things are giving. And there's a lot of demand in the defense also. Many people are
Yeah,
interested in.
yeah, yeah. There is a lot of you told about the channel state estimation. Yes, channel state estimation is really a problem.
It's a
It
big
is
problem.
problem for, and not only for that, for communication people, those who are working on the MIMO systems, and the receivers, they are working on that. Okay, so yes, we will look into that. How some collaboration possible on that side. Definitely.
Yes, sir. Yes. Good, sir. Good night.
Thank
So,
you. Thank you. Thank you again.
thank
Ah,
you.
I
Thank you.
think I think on 6th you are coming this side, so
Yeah,
we
yeah.
will look
We'll
forward to
meet
meet
actually.
you.
We'll meet. We'll meet. Definitely
Okay.
meet.
Thank you. Thank you.
Bye bye.
Bye.
Sir,
Good night. Good night. Good night.
Good night.
good night, sir. ଆଉ ଅଛନ୍ତି ଲୋକ